We're going to start our module 3. We're going to learn about machine learning and supervised classification in Earth Engine. This is one of the core topics in Earth Engine, and when you're doing remote sensing, a lot of your workflows will end up using machine learning, and for doing your analysis, you may have to do supervised classification. So we're going to do a deep dive, understand the concepts behind this process, and then implement the full workflow in Earth Engine. So far, we've been using code and we are been extracting computing indices. We are kind of applying some thresholds and trying to figure out what this pixel might be. But most of the work in remote sensing is to determine what does the pixel represent. So when you're looking at an image, visually you can interpret this, but when you want to analyze it, you want to know, is this pixel vegetation? Is this pixel built? You want to know what is there at the pixel. So that's the main task in remote sensing. And if you go by the traditional methods of doing thresholding, using indices as a proxy, it doesn't work all the time because Earth observation data is noisy. You can't have, if you just have this material in a lab and in a pristine environment, you measure the reflectance, then you can say, oh, I know this pure water has this much of reflectance. But in a real world scenario where you may have a lot of sediments in water, you have satellites in space, there's atmosphere there, there's noise in the sensor, you cannot apply this physics-based rules to your model, to your data, because it won't work with all the noise. And that's why machine learning is a great fit for Earth observation data, because machine learning is much more robust against this kind of noise. And instead of building all those rules to detect different objects based on the reflectance values or indices, you can just say, I will use machine learning models to determine how they can be separated from each other using some data as my learning object. Machine learning algorithms learn from data. So you, instead of defining the rules yourself, you say, here are some labels. I will tell you what each pixel is in my training data set. You go and figure out what is the relationship between the different reflectances and different land covers, and then you'll build a model, and then that model can be applied on noisy data, and it'll be able to correctly identify all the unknown pixels and their classes. So that's why machine learning has been used widely in remote sensing. Even before it was called machine learning, remote sensing people have been using this. I joke with people that, remote sensing people used to use machine learning before it became cool. If you pick up a book from like 80s, there'll be a chapter on supervised classification, right? And you'll find the same concepts here. It's just that nowadays we call it machine learning. There are kind of two classes of machine learning that you can use for remote sensing. The first one is unsupervised learning. This is a kind of class of algorithms that will take your data and without any of the input from your side or any labels, it will say, I'll try to group different pixels or different objects into the same categories. So it'll take different pixels and say, I'll figure out which pixels are similar and then put them into the same category. This kind of algorithms are called clustering algorithms that will help you find similar things. So you give an image, it'll say, I found this 5 different things in these images. It will not know which is what. This is where you have to go in for labeled and say, oh, this one looks like water, this one looks like agriculture. So this is kind of unsupervised method where you just go and find similar things. If you've heard of algorithms like k-means, those are the kind of clustering algorithms. Those are available in Earth Engine. You can use unsupervised methods. We have some really interesting examples of applying unsupervised methods on remote sensing data to do a lot of detections automatically. But more widely, supervised learning methods are used because here you can give a small number of labeled data and algorithms can learn how to detect those kind of labels in your data set. So you start with some data and say, I will go and find some pixels, some examples of different land covers that I'm looking for, and I'll manually label them. Either I'll hand label them, I'll do a field survey and figure out what those pixels are. And based on the data, you can build a model which will go and now classify and identify those particular land covers in unknown pixels. There are examples of algorithms like this called random forest, regressions. Those are kind of supervised learning methods. Before we dive in further, just want to clarify that machine learning is a different way of solving a problem. It's not inherently better or worse than a traditional way of doing things. The way you traditionally build your programs is you say, I have this data, I will compute some index, I'll apply a threshold and say anything greater than 0.2 of NDVI is vegetation. That's a simple program that you write, and you can term this program as an expert system. That means you used your knowledge coded the rules that apply and then detected a particular object or a class based on those rules. This is still fine. This is also still very widely used. If you do a good job, this kind of systems can work really well. If your output is dependent on only a small number of parameters, this method usually works much better than other methods. It also is very easy to explain. You say, I have some false classifications. Why did this happen? You can just look at your rules. You can look at your rules that you built. You can easily see why this didn't work for this pixel. But as you start to scale up, you say, oh, but I need to have now, instead of just 5 parameters, I have 1,000 parameters or hundreds of parameters that I need to learn from and then figure out what's output. So output depends on not just 1 or 2 or 5 or 10 parameters, but hundreds of parameters. Writing those rules can be cumbersome. It can also become very error prone and hard. This is where machine learning shines, where you don't need to really figure out the rules. You can say, here is NDVI, here's some labels, go and figure out how do you classify vegetation from this. It'll go and figure out the right thresholds automatically based on the labels it gives. Right? So you don't really need to worry about thresholds or even what input parameters are important. The algorithms are robust enough to go and figure that out themselves. And you can have many, many different parameters. So you can say, here are 100 different images or 100 different parameters that you need to learn from. Figure out which one you want to use to predict your output. But this requires label data. That means you need to have some labels that you have either manually or generated from some other data set, and you can learn from that. Both of this are okay. In real world, many people use a combination of both in their work, but just do not think that just because you're using machine learning, you'll get better results. Again, it's two different approaches. If you really know how to go from your data to your final answer, an expert system usually is much more easier and more accurate. If you have lots of messy data, your rules are unclear, but you can spend some time collecting and curating your data, then machine learning would be a better choice for that. When people come to me and say, I want to do machine learning, and I ask why, and they say, oh, it's going to solve my problems. I say, it's not going to solve your problems. It's just going to give you different problems. Right? So now it's not magic wand that you can just wave and everything will solve. It's just that you'll be doing different tasks when you're doing machine learning. You're going to learn what those is, and we'll go through a whole life cycle of a machine learning workflow. So you understand how to set this up and what are the different steps involved. Let's learn about supervised methods and how to do this in Earth Engine. This is the most widely used algorithms for remote sensing, where you start with some images and you perform a classification of pixels and you identify what class or object that the pixel represents. The process of classification is to turn your raw pixel observations into land cover classes or land use classes or objects, right? So you need to know what is in that pixel. You would start with an image like this, and at the end of your classification process, you want to end up with something like this, where you have identified what each pixel represents. Here, we have classified this into 4 different classes. We have built up, bare earth, water, and vegetation. So this one is great. You can probably visually interpret some of those classes, but then there are hundreds of thousands of pixels. I want to do some quantification. I want to know how much is the area of vegetation in the city. I can't answer this question unless I know really which pixels are vegetation, right? So for kind of doing any kind of analytical interpretation of this region, I have to turn this into a classified image. And this is where your machine learning methods will really help you and scale this to large regions and do this quite easily. Again, we need to do classification before answering any of the analytical questions. Even when we know what is the land cover, sometimes we need to say, oh, this is vegetation, but what kind of vegetation? So we need to further classify that pixel into what kind of vegetation. Is it agriculture or is it forest? Even for detecting changes, you say, I want to know what was the change in the city. I want to know all the water bodies that were lost between these 2 years. So first you need to know what are water bodies. Right, which pixels were water before, which pixels are not water before, water after. So again, for any kind of change detection also, you need to do the classification. We'll learn how to do this using machine learning and using the supervised method. In the supervised methods, you would start with an input image and you start with data. So machine learning algorithms need some labeled data. So we need to create those labeled data, which will collect. There are different ways of collecting labeled data, but this is kind of the first step in your machine learning project. So let's learn how to do this. Once we take the data, we'll train a classifier. once the classifier is trained, we'll apply it on all the unknown pixels because we'll have labels only for a few of the pixels. We'll go and apply this, and the model will predict what is the class at each of those pixels. We'll figure out how good is our classification. There are some analytical methods that will allow you to know how good is your classification. If you're happy with it, you can stop and say, here's my output. But typically, you would have to do this in an iterative process. You'll say, oh, I'm not too happy with this. You can try different classifiers. You can tune some parameters, or you can go and collect some training data. Because my model is not very good at separating out agriculture versus forest. Maybe I want to show some more examples. So you can go and collect more samples. And once you kind of do this a few times, and when you're happy with your accuracy of your output, you can stop and do some post-processing. So this is the full cycle of a supervised classification workflow. All of this can be done natively in Earth Engine, and Earth Engine is really ideally suited for this kind of work. And one of the most widely used applications of Earth Engine is to implement this kind of classification workflows. Let's go and learn this each step. So we'll start with an image of your region of interest. We'll learn how to collect samples, how to set this up. We'll train a classifier, we'll classify the image. We'll learn about all the ways to improve your accuracy, and then finally we'll learn about post-processing. The first step in your machine learning workflow would be to collect training samples. How do you collect training samples? Well, you need to have labels. We'll say for the pixels, you want to label each pixel and say this pixel is this particular land cover. So either you can go to the pixel and drop a point and say, here, I know this pixel is this particular land cover, or you can say I have some data as collected from the field. I have lat long and I have associated label, and you can also use that. Historically, people used to go to the field, and with a GPS receiver, you'd go and you'll stand in some farm or on a building, and you'll say this is the lat long, and you'll note down that this is the lat long and this is the land cover. The reason people used to go to the field is because our imagery was low resolution. You couldn't really see from image what that particular pixel was. So you couldn't just look at the image and kind of label the data. Over time, our resolution of images have improved. We have access to high resolution data, even a data set like Sentinel-2. You can identify many of the land covers just from the images. So you can just look at the image and label a few pixels just by visual interpretation. There are still certain classes where you cannot really look at from the images. Even if you look at Sentinel-2 image, or even you obtain high resolution images, like what you might see in Google Earth, even with those images, you can't really identify what is the crop. So if you want to do a crop classification, you have to still go to the field and say, I want to know what is the crop growing at this pixel at this time. So even with the high resolution imagery, you still may have to go to the field and collect some data. But for many classes, if you're able to interpret this visually, you can just sit on a computer and label them data. There are other techniques where if you have some high quality reference data, many countries, there exist good reference maps and high quality classification data. You can actually sample some data directly from there. So for example, if you want to collect data for surface water, there's this really nice data set called Global Surface Water, very high accuracy data set. You can just load this data and sample some random points. And you know already what is the land cover. You can automatically tag them as water. So depend on your region and the kind of classes you're looking for, you may be able to collect some data automatically based on existing high quality reference data sets. But even if you do not have one, many classes still can be collected very easily using this visual interpretation. We're going to do the first for today. We're going to focus on this particular method where we're going to create a Sentinel-2 image composite for your region of interest. We're going to visually identify different land covers and collect some training samples. This is the exercise that we're doing today. We want to take any region of interest and classify this into 4 different classes. Here are the different classes of interest. We're going to take a pixel and determine that each pixel is either urban, bare, water, or vegetation. This is the definition that we're going to use. Machine learning algorithms work best with numeric data since it's easy to do math with numbers. So we're going to assign a class number that will be used by the algorithms to assign the final value to that. So wherever pixel we are labeling that as urban, we're going to say this one is land cover 0. Wherever the pixels are bare, we're going to say land cover 1. Where there is water, we go to land cover 2, vegetation, we go to land cover 3. Again, this is a very broad definition. You can have more minor classes. For example, you might want to have vegetation of different kind of forest, agriculture, and so on. We're going to have a catch-all definition here just to keep things simple and make sure you are able to complete the exercise here. If when we're collecting data, there are certain classes that may be missing from your region of interest, you can skip that class. So for example, if you are trying to do land cover classification in, say, Saudi Arabia, there is no surface water. It's a desert, right? So if you just skip that, there's no surface water here. Also, we have people who are trying to classify Tokyo and they say, I cannot find any bare pixel. Everything is paved, right? So again, if you have such cases, you can just skip those classes and it'll be totally fine. What we're going to do is we're going to dive in and I'm going to start building the code to show you how we can go and collect this data. We'll dive into the code. We'll come back to this presentation and see how we can do the next steps. We are now starting in the module 3. We will start with the A script. I'm going to first go and show you how we can collect this label data for our region of interest. We have an exercise where you'll be doing this for your own region. But first, let me just demonstrate the process here. Here is a region that we are trying to classify. This is the city of Bangalore in India. We have taken the Sentinel-2. We are now working with the level 2 data. So this is surface reflectance data from Sentinel-2, applied some filters. We applied a cloud mask. So we're using the Cloud Score Plus mask. We've applied a filter. And as I mentioned in the previous sections as well, the way you would now work with data is you start with your collections, apply the filters to find images for your region of interest for the time period that you're interested in, immediately apply a cloud masking function. So you remove all the cloudy pixels. And then whatever you're left with, you can either do some time series work, or if you just want to get a cloud-free composite, you can do a median composite. So now we have our median composite, and this is our starting point of our classification. So we have this really nice median composite for the city. You can see this is 10-meter resolution data, so we can see a lot of things from here. So for example, I can easily see that this particular region is a water body. I can also see that this is built up area. I can see some roads, I can see houses, I can see some bare pixels. I can't see like cars or small buildings, etc. But that's good enough. So for the land covers that we're interested in, we can just use this image as a reference to identify what those pixels are. And we need to label, let's say 10 pixels per class. So we are interested in doing a 4-class classification. So we want to turn this image into images where we have classified each of those classes. So here are the 4 classes that we are interested in. So let's just collect data. The way I'm going to start is I'm going to use the drawing tools that come with Earth Engine, and we're going to select a point tool. First, we're going to collect data for some urban pixels. So urban we are defining here is any pixel that is built. So any impervious surface, anything that is built up. So buildings, bridges, all of those will come under this class. Here, I can go zoom into a region, and once my image loads, I can see all of this looks like built regions. If you're not sure, say I just want to confirm, you can switch to the satellite view. And when I turn off this image, you will see the Google Earth high resolution image. And I can kind of confirm that all the blue pixels I see are actually indeed built up pixels. You can use this high-res image as a reference, but not for classification, because this is just an image that is coming from the base map. You don't have analytical access to this data. Also, this image may be older or newer than the image you're trying to classify. So when you are collecting training samples, make sure you always use the image that you are trying to classify as your reference image. But just if you're having trouble interpreting the pixel, you can use the base map as a reference. So I'm going to say, okay, whatever this pixel is actually an urban. And I want to collect more samples. So instead of just putting that as geometry, I'm going to save them as a feature collection. And I'm going to name them as urban. And I'm going to change the color. So I can say this is urban. I can go and collect some other points and say these are the 3 labels I've collected. All of these 3 are urban pixels. How do I tell my model that this is an urban pixel? We have to say this is the class 0. So when we are collecting data, we save it as a feature collection. Remember, feature collections can have properties. So this is like if you have a shapefile, this is your column attribute table. we can use that and say, let's just store the value here. We're going to use the property called land cover and assign it the value 0. That means every point I collect inside this feature collection will be assigned the value land cover equals 0. You can use anything. The script that we are using assumes that you have a property called land cover where you have assigned 0, 1, 2, 3. Okay, so we're going to use 0 for the urban class, and we can go and collect some more samples. The idea for this is to show the diversity of different landscapes. You want to say, even I consider the stadium as a built-up. So if you want a model to classify this, you need to train the model with the data. So you can say, here is another example of a built class. You can also use some roads and say, even roads I would consider as built-up class. So you go and find some examples on the road, and you can drop some samples. One common thing that comes up is, what if the road is covered with tree canopy? Well, the sensors have only captured the top of the pixel. That means there's tree canopy there. So if you label that as urban or built, the model will get really confused. It says, this looks like vegetation. So again, for those pixels, you can just class the example as vegetation. So whatever you can see in the image, this is what you should use as your labels. We can do this again for a city like this. Even 10 samples are more than enough for doing your classification. As you scale up to larger regions, you may need a little more labels, but usually your requirement of labels would be in hundreds of samples per class, even for very large scale classification. And if you did this well, if your sample is accurate and they capture all the diversity, the model will learn how to kind of identify those pixels in your data, and they'll be able to go and correctly predict the class of each. You can continue doing this. You can say, I'll want to collect the samples for the next class. I'm going to add one more layer. Same thing, we're going to say this one will be the bare samples. We'll change the color, add the property. This time we'll say land cover is 1. So we are using 0, 1, 2, 3 is our properties. So 1 will be bare, and we're going to go and find some bare samples. So again, you zoom into a region. We are defining bare as anything that has exposed soil. So something that doesn't have built-up regions, doesn't have vegetation on it, you can use that as a bare sample. And you can go and find a few examples. Again, you would want to find diversity of samples. Maybe different parts of the city have different soils. So you may want to go and find those. Again, you can see some of this bare soil might have slightly different structure. So you go and find all the examples. And you can keep going and collect samples for all of the remaining classes. And that will be our input to the model, where we now have collected samples for this data. So this is the samples I've collected. So you can see my samples are well distributed in the region, and I have collected samples for these 4 classes, approximately 10 examples for each of this. And now I say, okay, I have my labeled data. How do I actually go and build a model and predict the class? So when you're collecting samples, one question that might come up is, how many samples are enough? And as with many things in machine learning, there is no theoretical answer. A lot of this is based on practical experience, and people have tried different things. In general, the thumb rule that you can follow is 100 points, 100 samples per class is a good starting point. The more is always good, but if you have, obviously you'll have limited time and resources. If you want to focus on, I would say focus more on quality, not quantity. So 1,000 bad quality samples is way worse than 50 high quality samples. Right? So when you're collecting data, make sure each point you're dropping the samples, each corresponds exactly to the class. When you're collecting your labels, the label should be pure classes. That means, let's say you have a pixel which is water covered with vegetation. What should I label that? Skip that. Do not pick that pixel as your reference data, because that's confusing. Once you have a pure water pixel and a pure vegetation pixel, the classifier will decide what that pixel becomes. So always take pure pixels, high quality reference data that is more valuable for machine learning models than a bad or error prone samples, because machine learning models tend to kind of treat your samples as golden data. That means it will say, I will try to really learn from it. This is the truth. And if you have errors in your sample data, then your models will not perform very well. Another thing to keep in mind is the balance of the samples also matters. Many algorithms will give more weightage to classes, to the land covers with high number of samples. So in this case, if I had 1,000 urban samples and the classes were very low, the model will think the urban class is more important and it'll give more preference to an urban class. And we don't want that. So a good practice is also have a balanced number of classes. So if you have 100 samples in all classes and 500 in one, discard the 400 samples in the one. Try to keep it balanced. The drawing tools also have the flexibility to delete or move the samples. So for example, if I collected the sample and I said, this is something I don't want, I can use this hand tool. This is the pan tool. I can select the point. Once I select the point, it'll give me option. You can drag to move or delete it. So I can just move this and say, this is the correct location, or I can just delete it completely. You can also change the layer and say, I want to now collect data for other particular class. So again, while collecting samples, you can say, I collected bare samples, but as I was collecting, I saw a really good example of a built class. I can always switch to this class and drop one more point here. And I can always, if I made a mistake, I can delete all of that. We have our samples, we have our label data. How do we go and train a model to predict the class? Let's learn the next step in our process. Once we have a label data, we need to train a classifier model. Here we have collected training samples. We now need to pick which model we'll use. Earth Engine has many different machine learning models that you can use. You can pick the model that you want to use and train that model with your training samples and say, please learn what is the relationship between your input data and the class. It'll figure out the relationship. And once the model is learned, you can go and say, now I have so many unknown pixels, go and predict what would be the land cover class based on the training data that I supplied to you. And then you have your classified image. Which algorithm to pick? We're going to go and first understand how these algorithms work. And we're going to learn about 3 different algorithms from simplest to most complex and see how they differ. To kind of visualize how the algorithms work and to kind of understand the steps, let's say we want to focus on a binary classification. We're going to classify this region into water versus non-water. This is just for the purpose of understanding how would the model learn and predict the output class. Same thing would work for any number of classes. But again, for visualization, we're going to use a focus on 2 classes. So first step is training samples. Let's say we collected 100 samples, 50 water and 50 non-water samples. So this is a step that we already done. We have this table data. We have to create a table like this as an input to our model. So for example, we have our labels. So let's say we want to do a binary classification and we have our samples that we have collected. At this point, we only have the lat long and the class. So we just say I have point and I have associated class, water versus non-water. For machine learning models to learn, we need to give some inputs. In our case, input would be the reflectance values of different bands. So that's the pixel values, and we need to turn those observations into a class. So we need to create a table like this where we have for each point, we need to have a class along with all the reflecting values at that pixel. And again, we can use as many inputs as we can. We can use all 13 bands of Landsat, or we can use all 13 bands of Sentinel-2. We can use other dataset for visualization purposes. To make it easy to show this in a chart, we're going to focus on just 2 parameters. So we can see this output in the chart. So let's say we select 2 bands and say, this is the value of the green and NIR reflectances at those pixels. We collected 100 samples. We already labeled them. Is this water or not? And we have extracted the values of those reflectances at those 2 bands at each of the points. And we have a table like this. This table becomes your input to your machine learning algorithm. A lot of your task will be to generate a table like this for your classification task. A set of inputs and labeled output. And once you generate a table like this, you can train any model that you want. So this is the data. So if I plot this on a chart, you can see I have the green and NIR values and I have label. If I plot this, this is what the data looks like. This is what my label data looks like. Water generally has low reflectance in NIR and high reflectance in green band. And if I plot this, I can see this pattern. But I need to know now, how can I build a model that can learn from this data and given an unknown value can predict whether it's water or not? We can learn about the 3 different techniques. We'll learn about an algorithm called SVM, which is the support vector machine. We'll use another algorithm called decision tree, which is the most commonly used algorithms nowadays. And then we can also use a deep learning model using a neural network, which we'll do in our last module. Let's say we have this data and we want to train an SVM model. How does it work? The way SVM would work is, given your data, the job of an SVM is to find a line that will separate water versus non-water pixels. So given the chart, SVM would say, I will learn from the data and find the line that would separate water versus non-water. If you have input data in, say, 10 dimensions, you'll find a plane in 9 dimensions that will separate that two things. So you can imagine if you have 3-dimensional data, it says I'll find a surface where above everything is water, below everything is not water. That's what the job of SVM training is, to find the surface, to separate out the two classes. So if we give this 2-dimensional data to SVM, the model will learn from this data, and the output of the model training would be a line like this. Say, I figured out that based on this data, that this is the best line that you can use to separate water versus non-water. Once this model is trained, you can say, now go and find what is the class of every other pixel. You'll go and find an unknown pixel. Let's say I have a new pixel that I'm trying to predict. I have my trained SVM model. If the pixel is here, so I look at a pixel, I find its green value. So this is the green reflectance of the pixel. This is the NIR reflectance of the pixel. If the pixel is here, it's going to ask SVM, what do you think this is? SVM will say, this is below the line, so I'll label this as what? We'll move on to the next pixel. You'll find the reflectance of that pixel and say, oh, this is the reflectance of this pixel in green and NIR band. This falls above the line, so I'll make it mark it as not water. And it'll do this for every unknown pixel, and then you have a classified image. So the training part will be to figure out this plane separating these classes, and then in the prediction time is going to use that plane to figure out where the pixels are and classify them accordingly. There are a couple of questions. How is this line drawn? So this line is not drawn. This is a mathematical representation that you'll get. So once you train a model, you'll have a mathematical representation of this line or a hyperplane. The line, you can imagine this only in 2 dimensions, but if you say I have my input data as 12 bands, this will be a 11-dimensional plane, which you can't visualize, but you can represent that mathematically. Right? So you'll just get a mathematical formula as the output of your training. And then you go and run this formula on all the unknown pixel, and you'll get your answer. So SVM is one of the older machine learning algorithms. It's quite simple. It's good for kind of a binary classification, water versus non-water, forest versus non-forest. It used to be used more, people in remote sensing used to use it quite a bit, but nowadays everybody uses newer models which are based on decision trees. So let's learn how decision trees work. Decision trees are designed for multi-class problems. So you can, instead of just binary classification, you can say classify this to n number of classes. It will also work well. Instead of just separating this using a hyperplane, the decision trees actually build a flowchart-like structure. And at each step is going to determine what is the possible class by looking at the rules that get figured out based on the training data. It's currently the most popular machine learning algorithm for remote sensing data. It's easy to interpret. You can also use it for both regression as well as classification. So when you're doing machine learning, for now, we are classifying the pixel and saying, this is class 1, this is class 2. But you can also use this to predict numeric values. You can say, I'm going to predict what is the biomass at this pixel. I'm going to predict what is the yield at this pixel. And again, you can use this tree-based models to do both classification as well as regression. Let's see if the same data that we have, the same table that we have, if it is given to a decision tree model, how would it learn from this? So again, same table, we have the input features, green and NIR values, and the labels. We give this table to the algorithm, it'll go through its process of training. At the end of training, it'll generate a flowchart like this. And again, this is done automatically. You don't have to do this flowchart. You just say, this is my table. As part of the learning process, the model will generate this flowchart. It may generate a flowchart like this, saying, first step, look at the value of the green pixel. If it's less than x, do something. If it's greater than x, do something. What is x? Well, it'll figure out based on the data. We don't need to give this x. It'll just say, based on your data distribution, I found this value of x. If it's greater than x, check the NR value. If it's less than y, do something. Greater than y, do something. It'll keep doing this for all the parameters and it'll build this flowchart. At the end, you'll assign a label to it and say, now if the input had green value greater than x and NI value greater than y, it's likely not water. This flowchart would be generated automatically based on the training data you gave, and this becomes your model. Now, when you're trying to predict and say, okay, you learned the data, you generated your flowchart, go and run this on each pixel. For every unknown pixel, let's say I have one pixel, I want to classify it. You look at the value of this pixel in the green and NR band, go to the flowchart. Is it green greater than X? You say yes, you come here, check the NR value. Is NR less than Y or greater than Y? If it's greater than Y, it's not water. And you do this for every pixel, go through this tree at each pixel and assign the class. The advantage of this method is, one, it's easily interpretable. You can actually see the trees. Even when you train in Earth Engine and you print your classifier, you'll be able to see what tree it has generated. So you can interpret how the model is learned. It's also in scale to many different classes, many different parameters, and quite easy to use. One problem with this kind of model is these models tend to treat your input training data as really gold, and it's going to try and build a model that exactly fits your training data. They're not very robust against the outliers in your training data. So let's say you have, and again, even you made a mistake, or even our Earth observation data is noisy. Let's say you had one pixel which you had labeled as water, which has this value. So it has got a high green value and a high NR value. Either it's a mistake from your side, or it's just the noise in the data that has ended up this. You still want your model to look like this, right? You still want a flowchart to look like this. Just this is outlier, don't worry about it. Instead, what your model will look like is, it'll say, oh, this data, I will try to reproduce this. So it'll say, keep doing. You're going to now go and say, if NIR is greater than Y, check if NIR is greater than some other Z value or less than Z value. It's going to create one more threshold like this. It's going to create one more threshold and try to say, if the pixel is right here, that is water. It's going to keep going and generate a very complex tree for you. This kind of thing is called overfitting. It's a big problem in machine learning where your model will try to reproduce your training data exactly in the model and not really learn the pattern of the data. Decision trees are great, but they have this overfitting problem. So how have people solved it? They've solved it with an algorithm called random forest. What people have found that instead of building one tree for the model, one model for the data, you can actually build multiple models from the data, but not show all the data to all the models. So instead of building one tree with all the data, there is an algorithm, a variation of a decision tree, which says, I will take a random subset of the data. Let's say you have 1,000 points. It'll say, I'll only take 500 points for now, randomly selected, train a model. It might overfit to that 500 dataset sample, but that's fine, because then you take another random subset of 500 samples, train another model, and you keep doing this. You train hundreds of models like this. So you have 100 models. Each of them have seen different subset of data. They've learned the pattern in that subset of data. They might have overfit to that, but then at prediction time, you ask all the 100 trees that you train. Say, what do you think is the correct answer? Maybe 80 of them will say this is water, 20 will say not water. You just take the answer of the majority output. Say 80 of my trees said water, so I'll label this as water. This kind of method is called ensemble learning, where instead of just building one model, you build multiple models, ask everybody to predict the answer, and you just take the majority output. This surprisingly works really well. It solves this overfitting problem, and it is like wisdom of crowds. Like if you ask enough people about something, you'll converge on the right answer. Right? So this model also works in a similar way, and this is currently the best performing model for classification and also for doing machine learning, where you use random forest model, which is just a collection of decision trees trained on random subset of data. And this will give you much better performance than either single decision tree or other models like SVM. I wanted to give you a little bit more theoretical understanding so that when you want to pick the model, when you want to debug some model, you may know what's going on. In Earth Engine, this is one line of code. Just a train a random forest model and you're done. That's it. Okay, let's see how this works in code. We're going to go back to the code. At this point, we have our Sentinel-2 Cloudfree composite that we have created for our region of interest. We have collected labels for 4 classes, and we have those. This is still not our input training data. Remember, for getting our training data, we need to generate this table first. For each of the samples, right now, we only have label, class. We still don't have the reflectance values. So we need to extract those. First, we have this 4 different feature collections. Let's just merge them. It's just easier to work with 1 feature collection than 4. So we'll just create a new variable called GCPs. GCPs stand for ground control points. I think this comes from the kind of old school remote sensing where we have to go to ground to collect samples. Still going to kind of continue to use this variable name. You can use different one if you want to. So let's just say we have this 4 collections. We're going to use the merge function to merge all of them. We'll do merge bed, merge water, and merge vegetation. And if I print GCPs, you'll see that this is a single feature collection with 33 samples. At this point, each of the samples have a property called land cover, which is holding the class value. And there are different values based on what we have labeled this. We now need to know what do we train this model with. If I look at my image, this composite image that we are using, this is a Sentinel-2 composite, and we have 12 reflectance bands, band 1 through band 12. And if I look at each pixel value, you will see that we have those pixel values, which are the reflectances in different wavelengths. This can be the input. So we can say, look at the values in each of the bands and predict that this is class 1, 2, or 3. So this becomes our input features that we want to train the model by. So we want to extract the values of each band at each of those locations. So Earth Engine has a function to extract pixel values at given points or polygons, and it is called the sample regions. So we'll extract our samples. We'll say, take this composite image and use this function called sample regions. We'll use control space to autofill all the parameters, and we can use a dictionary to specify. We'll say, I have this composite image where you want to extract the pixel values from. We can give this collection. GCPs is our collection of training samples that we have. It is going to, if I look at my feature collection, it'll say, what properties should I keep in the output? You may have a lot of other properties that you don't want to use for machine learning. So we say my property that I want to have in my output is this land cover property. And again, in our code, we are using land cover as a name. You can use anything. You can say this property I want to use as class or anything else. Just make sure you change that in the code to keep that property. Scale, at what resolution do we want to extract the pixel values? Again, always use the native resolution. This is, as I mentioned, this one will give you the highest accuracy with the least amount of computation. And we're going to use the 10 meter scale. That's the resolution of Sentinel-2 bands. And we can skip other parameters. Let's print the result and see what we get. So we started with this 33 labels. We just had one column called land cover. After extracting those band values from this composite image, we'll now have the pixel values at each of those locations extracted and available to us. This will be our table that we'll use for training our models. If I look at this, you can see there are the same 33 samples, but now there are 13 properties. We have at each location, these are the input reflectance values, and then this is the class. The job of the model is to say, I will learn from these values and figure out what is the relation that I can learn from this to predict that this is class 0. Similarly, I have to learn from this and say if the pattern looks like this, I need to predict land cover 2. Right? So it has to learn this pattern of that from the inputs and try to predict the output here. Let's train our model. Switching to the docs. All the classifiers in Earth Engine are under each classifier module. So if I look at each classifier, these are the different classifiers that are available to you. If you're coming from a traditional remote sensing world, you might have used KNN, for example. That is a popular desktop-based software. Use KNN as a classifier. If you want to use SVM, it's available here, so you can use that. The random forest that we're going to use is available as this algorithm. There are some other algorithms. For example, CART is a single decision tree. So if you want to still use a single decision tree, you can train a CART model. There are some newer algorithms like gradient tree boost, which people have tried and also performs equally well or sometimes better than random forest. So this is also something that you can try. The beauty of Earth Engine is you can just pick one, build your code, run it, see the output. If you don't like it, just change one line of code and you get a different output. Or you can just copy paste and run code for all the algorithms and you get out. So again, you can decide which one you want to use later on. Right now, you can pick anything you like. If you don't have any preference, random forest usually performs really well. So in absence of any other information or a preference, you can start with random forest. Let's start with a random forest and train the model. So we'll create a classifier. We'll say classifier random forest. There are so many parameters that we need to give. So for example, this number of trees will tell you how many trees it would train for based on training data. We can say train 10 trees, 100 trees, how many trees you want. The bag fraction is what is the subset of training samples it would use for each of the trees. By default is 50%. You can adjust that a little bit. For the model, you can see there's only one parameter which is required. Everything else is in italics. We can skip this for now. We can figure out how to find the optimal values later on. For now, we'll have to pick some value. How many trees we want to train? Well, again, as with everything in machine learning, there's no theory. There's no theory that says, use this many number of trees. In the older times, people were limited by amount of compute that you have. The more number of trees, the more compute you need. In Earth Engine, really doesn't matter how much. You're not limited by compute. So I've used 50. Why? Because I just feel like this. Right? We'll figure out what's the right number of trees later on. This process is called hyperparameter tuning, where once you've done your whole process, you can go and try different combinations of different parameters and find the one that works best for your data. For now, we'll just pick 50. We'll see if that was a good choice or not. Later on, doesn't really matter. At the end, we'll just figure out the optimal parameter. So we have a classifier that we have initialized, and there's a function called train that we have to call on this. So on a classifier, we can call the train function to train the classifier. Autofill to fill all the parameters, and then we can train. So what are our training features? So these are training features where we have this as input, and this is the class that we want to predict. So we have the training variable containing our training samples. Class property. You need to tell the classifier that out of these 13 properties, which one is the class, which one it has to predict. And we said this is the land cover. So again, if you're using a different value, a different name for your labels, you have to change it here. Input properties. What are the inputs that I need to learn from? And we will say, learn from B1, B2, and so on, right? So B1 to B12 is all your inputs that you need to use to learn and predict land cover. Since this list of values was sampled from a composite, we can use this shorthand and say, I don't need to type this B1 through B12 manually. There's this nice function called band names, which will give me the list of bands for a given image. Since we had sampled it from composite image, the values will be the same as the band names for that. So we can just use this. It'll give me the list of bands that input image, and we can use that here. You can also do this manually if you want it. That's it. So at this point, my classifier is trained. So it would do all the training part. It'll take on the sample, do the subsampling, and train 50 different model trees. And now I'm ready to predict. So I need to classify my image. So I have this composite image, which has got hundreds of thousands of pixels. We have labeled only 33 pixels. Now we want to say there are a lot of these unknown pixels. Take each of those pixels, look at the input pixel value. So at each input pixel, we have this 12 values. We'll ask the model, can you predict what is the class here? The model will do this for every pixel, and then we'll generate an image, which is our classified image. So let's do this. There's a function called classify, which we can give our trained classifier, and we'll generate a classified image. And we can visualize this. Let's have some viz params. So we'll use the class viz. We are trying to visualize the classified data. So the range of values will be just 0, 1, 2, or 3. Only 4 values. It will be one band image with just 4 values. So the min would be 0, max would be 3 here. And we can give a palette just to assign different colors. You can use any colors that you want. We're going to use this color palette. This one is a colorblind safe palette. Again, I've got this from Color Brewer. You can ask for N class palette and you'll get different colors that you can use here. Let's add it to the map. We'll take our classified image. And again, I've not clipped anything so far. Again, it's a good practice always to clip things at the end or while displaying or only while exporting. We'll have our class viz as the visualization parameter. And then this is the classified image. And we'll run this. And what our engine is doing at this moment is it's now taking each, first is training the classifier, and then taking each pixel, asking the classifier to predict the class. It's doing this in many, many machines in parallel. And as you can see, as the output is being generated, it's being streaming from the servers. And in just a few seconds, we have our entire city classified. It has predicted what is the class at each of those pixels. And if you zoom in and kind of visualize the result, you can see it's done a fairly decent job just with small number of samples. And by training this model, it is able to now determine with a reasonable accuracy what is the class of each of those pixels in this region. If you've never done classification before, this might be like, oh, this is cool. If you have ever done classification on desktop software, this is mind-blowing, right? Because on a desktop software, this is typically takes a few days to see the result at this scale. So seeing this interactively is something that's kind of very new, and this is kind of shows you the power of Earth Engine, where now instead of focusing your efforts on kind of data processing or figuring out how to compute this, you can now try things like, what happens if I add one more sample to my data? I can add one more sample, rerun the whole process, and I can see the result. Or what if I want to try SVM? So for example, I'll say I want to try a different classifier. I'll want to use SVM and just run it. So I change this classifier. Earth Engine is now training SVM classifier and predicting my results on using this. And you can immediately visually see the results are significantly worse than running forest. But again, you can try different classifiers interactively and see which one gives you better results for your data. And again, this is not a final classification. This is the first cut. Remember, it's an iterative process. We're going to do a lot of things to improve our results. We're going to change the different features that it can learn from. We're going to change the parameters of the model. We're going to do some post-processing, and finally we'll have our result. But this is a kind of first pass. We have our code set up, we have our samples ready, and now we'll start iterating to improve this classifier. Instead of many, many small exercises, you have a big exercise where you have to do this for your chosen city. You'll pick your city of choice, you'll collect your training samples, and then we'll see how well you've done. And we're going to rest of the module is to help you improve that classification using different techniques we'll teach you. We've learned how to implement a classification workflow. We collected samples, we trained a model, and then we classified the image. Let's try this for your own region of interest. We'll do an exercise now. Vigna, you can explain the next exercise.
For the exercise here, you see that we have this code. We are having this geometry, and then we are trying to filter this general collection for 2019. And here is the whole collection and applying cloud mask. And here we have this composite. This is the median composite. And if you just delete this geometry and create a geometry at your chosen location, you will see composite for that region. So I'll just demonstrate again on the region that I'm familiar with. And here I will just create a new geometry. And I'll just run the code and I'll see the composite over here. So that is the first task that you are going to do. just create geometry at your chosen location and you will see composite for that location. And then you will start taking the training samples for these classes. We have the classes and the values given here. So we will create these many feature collections. Let's start with a new layer. In the setting, we will call it feature collection, and we are doing this for urban class. So just rename this and have a land cover property. So this is the property name. Name can be anything, but here in this code, we are going to uncomment a few lines of code to do the further processing. So let's keep it land cover, and this is case sensitive. So it should be spelled exactly like this. And let's assign the value 0. Here, this color is for the markers, the points that you take. So you can just change the color here, and the points that you take for this particular class will appear in that color. So let's start this. Zoom in to some region and you will see, let's wait for the image to load, and these pixels look like urban. So we will just take a point over there. Likewise, just go to another region, take some roads and features like that, and take point over that particular road. So, and always wait for the image to come. You can take the background of this high resolution satellite imagery for your knowledge, but always take points on the features that you see in the Sentinel imagery. So this is urban feature. Likewise, we will create another layer and again, we'll do the same thing. This is a feature collection that we want to do. This is for a where class. You can say, I want to show this in gray color, the points for your identification only. And again, set the property, land cover property, the value day1, and let's take samples for this particular class. Yeah. So likewise, we will take samples for water as well as vegetation classes. And as we already learned that you can just switch between layers. So while taking the samples for say bare land, you feel like taking sample for urban and it looks like an important feature to capture, then you can just switch to that layer and take the samples. Likewise, you can just switch to that and take a sample. And then you can also use this pen tool to shift your taken sample or to delete the sample. And likewise, you can just generate this 4 feature collection. And now we have the code for merging that, training the collection, training the classifier and applying all the techniques and finally generating the classified image. So once you finish with all the sample collection, you can just uncomment these lines of code and then run, and you will see the classified image for your region. So try this, try and take well-distributed points. So I was just demonstrating, so it was on the small region, but always take well-distributed points in your region.
Let's start exercise 1C. All of you can pick a region that you know, draw geometry first and take your training samples. While you are taking the samples, we have some tips that you can keep in mind. I'm going to display that. When you are taking your training samples, make sure you take well-distributed points. You should have points all across your chosen areas. Main confusion a lot of people end up with this kind of classification is a lot of your roads look very similar to water in the spectral space. So the classifier may label some of your roads as water. So make sure you have enough examples of urban points on roads. So make sure you take those. Once you're done, you have to uncomment. So there's bulk keyboard shortcut control / for bulk comment on comment. You can use that. And once you're done, you can uncomment, run the code to see the classification for your city. 10 points per class should be enough. But if you, after running the classification, you can see if there are certain mistakes that the classifier has made, you can go and drop some more training samples. You can say, oh, this is an urban, my classifier mistakenly classified this as bad. Go and drop an urban training sample there and rerun the code to improve your classification. When we implemented a basic supervised classification workflow, we were able to get some results and we were able to interpret this visually. Some of you might be happy with the results. Some of you may be saying, oh, I should make it better. But if you always have to evaluate this visually, then it's not very robust. We need a way to evaluate this in a quantitative manner so that when we make some changes, we know that have we done these changes and has it improved our classification. So let's learn some quantitative methods for evaluating your model's performance on your results. So far, we've done this where we have taken some training data, trained a classifier, and classified the image. And we visually interpreted it, but now we will learn how to do the formal accuracy assessment. The most commonly used method in machine learning for accuracy assessment is called the holdout method, where you have your training samples and you say, I know what is the correct answer to this particular pixels. So when you have labeled the pixel, you say, if this was the pixel, my class is 3, and you have that correct answer. So you have your training data where you have manually labeled, and you know that these are the right results for those particular training samples. Initially, we trained all our model with all our training samples. But now if you want to validate our results, we can say we'll not use all our samples for training. If we had 100 samples, we'll only train the model with, say, 50 samples. We train a model, we'll tell the model that we only have 50 samples. Go and learn from it, do your thing, classify the image. Once we have the result, we have other 50 points that were remaining where we already know what is the correct answer. We'll go and check what did the model predict at those locations. So we'll take the remaining validation data, say at this 50 locations, I had labeled this urban, and if my model classified that as bad, that means the model got it wrong. So I can check the model's performance against the label data that I've used in validation. And using this, we can now get some measure of how good the model is at predicting unknown values where we have already labeled the data. The way you would assess this is you generate something called a confusion matrix with the data that you had put in the validation data. Using that matrix, confusion matrix, you can compute all of these different numbers. Depending on what you want to do, you can use multiple of those. The most commonly used metric is the overall accuracy, is out of how many samples we had. Let's say we had 50 samples that we reserved for validation, and we check out of 50 how many the model got it correct. If 40 out of 50 were correct, it was 80% accuracy. There's also something called F1 score. This is more commonly used in machine learning practice, where you take the precision and recall and then take the average of that. Remote sensing practitioners typically use overall accuracy. Machine learning folks typically use F1 score. You can compute both in Earth Engine. I'll show you how to do both of those. When you generate a confusion matrix, this is what it looked like. On the rows are your label data. So let's say you had reserved 50 samples for your validation. Here is the classes that you had assigned. So that means this says there are 43 samples where you had labeled that as 0. On the columns is the model's prediction. So for those 43 points, the model also said it was 0. And that means everything that is in the diagonal are the points where the model got it correct. Anything that is not in the diagonal is where the model got confused. That means there are 3 points where you had labeled 0, the model predicted 1. And now if you just say, tell me the ratio of all the samples in the diagonals versus the total samples, that's your overall accuracy. Similarly, you can do it for each row, saying that there were total 46 samples. I had labeled as 0. The model could find only 43 correct samples. And that's called the producer's accuracy. You can also do it by column and say there were only 43 samples which were 0, but model kind of found 5 extra. And that's called the consumer's accuracy. These are also precision and recall in machine learning terminology, but you can kind of compute this and they'll give you an idea of what classes perform well, which classes where the model needs improvement on that. Let's go and compute this in Earth Engine. For folks who are coming from machine learning background, you'll notice that the confusion matrix is kind of inverted. If you pick up a machine learning book, in machine learning, the ground truth will be the columns and your predictive values will be rows. This is what remote sensing folks have been using for 40 plus years. Machine learning folks use kind of the inverted version of this. I'm going to keep with the remote sensing version. But if you're used to machine learning, you say, why this looks odd? Because we are using a different one. Again, both kind of fields evolved separately. There was different methods and terminology, but again, they're doing the same thing. So just a note for folks who might think that, I typically get comments on YouTube where saying your confusion matrix is wrong. So it's not wrong. It's just I'm using a remote sensing version of that. Let's implement this in our script 2A. We have implemented the basic supervised workflow, but for a larger region. So now we are working for a larger region here. This is like one of the river basins in south of India. We have a lot more training samples. And we have implemented the basic supervised classification with a random forest, and we have this classification. Let's look at our GCPs. If I print the GCPs.size, you'll say there are 447 GCPs. So now we have 4 class classification, but total we have 450 points, so roughly 100 points per class. And that's also a good recommendation to start with when you start a project. 100 points per class is a good starting point. So now we have enough samples that we can say, I don't need all of this. Maybe I'll split this into 2 parts, train my model with some data, and remaining data I'll use for validation. Here, I'm going to take my GCPs. So we have 447 samples, and now we're going to split into 2 parts. So I want to take some samples. For this one, let's do a 60-40 split. So 60% for training, 40% for validation. Again, people use 70-30, 80-20. If you have a lot more samples, you can use 50-50, just have more samples for validation. But if you have less samples, 80-20 should also be okay. Now I want to split this. How do I take 60% of this samples for training? I can do a simple saying that, first 60% would be my training, but that might include some biases. Maybe I have first 60% only covering certain landfill classes, or all the first 60% samples are in south of my city. So an important part is we need to do the split randomly. So there are no biases involved here. So we need to do a random split. If I just print my GCPs, you'll see that this is a feature collection where I have collected my samples, and we have this property here. There is a function that we can run called random column. This is a function designed or adding a random property to a feature collection, where if I run this and see my feature collection, you'll see that each feature now has another property called random with a random value assigned to that number, to that feature. And it has a random value from 0 to 1 that is assigned with uniform distribution. And that means each number from 0 to 1 is equally likely to be there. Let's look at the documentation for the random column function. Here you can give a feature collection and say generate random column. The default distribution is uniform. That is, all the values from 0 to 1 are equally likely. And that means you can have, if you say, what is the probability of a number being 0.5? It's 1 by 100. There's also a normal distribution if you want to use that. Here we have just uniform distribution. So we can say, if I want to take 60% of points randomly, I can use this and say, if my GCPs have this random column, I can now filter it using this and say, give me all the features where the random value is less than 0.6. And this will give me roughly 60% of points, but randomly, because there's a uniform distribution, there's equal probability of all the numbers to be there between 0 to 1. So if I say, give me all the values 0.6 and below, that will give me all the training samples, which are 60% roughly. The remaining one, I can do validation, and I can say 0.6 and below is training, 0.6 and above, so I'll change this to GTE. So 0.6 and above will go to validation. And let's check if this worked. I'm going to print the training samples. And we'll print the validation one just to check what is the distribution that we got. I have a typo here, so let's just fix that. And out of 447, you can see we got 247 samples as training and 200 as validation. And this was split randomly, so we were able to now be assured that we didn't include any bias into this. We can also change this. If you wanted 70-30, we would go up to 0.7 and say 0 to 0.7 random values will go into training, the remaining one will go to validation. And so we can adjust the ratio as we wanted. Let's keep 0.6 for now. Now we have our training GCPs randomly selected. We'll say, let's train the model with only those. The model should never see the validation GCPs. So now when we are running our classifier and training it, we are only extracting data at training GCPs, and we are training a classifier and we are predicting the results. So far the model has been trained only on this subset. It has not seen those 200 samples that we had. And now once the classifier finishes and predicts all the values, we can check what was the model's answer at those remaining samples. So we have our classification. We can visually see it, but we want to assess how good it is quantitatively. So let's just do our accuracy assessment. I'm going to show you the remote sensing method for accuracy assessment. If you see the full script, the B script, there is an alternative machine learning method for accuracy assessment. They give exactly the same answer, but with a different approaches. I'm going to show the remote sensing approach since many of you might be familiar with that. You might have done this in your desktop software, so it will feel more familiar. In remote sensing, you first classify your image, right? You have already predicted the result at every pixel. So you already have your model's prediction. If you want to know how do they compare with your labels, you can just sample your composite. So I can just say my validation data will be take my classified image, which has the model's prediction, where the model's already predicted all the pixels. I'll take and I'll sample this. We'll use the sample regions function and say, sample this at my validation GCPs, where I only have the label. So I have my labels, I have randomly reserved those points, check what was the answer. And if I just do this and print my result, I'll print both the validation GCPs first and the output, so you can see what we did here. So we had 200 validation samples, and since we had manually labeled them, they had only this land cover property. Right? So we had labeled and assigned those labels. Now, when we sample the classified image, we can say, oh, we already have the label that we assigned. Let's see what did the model predict at that location. So once we check, we'll see that the land cover is what we had labeled. The classification is the classified image that the model produced, and we sampled from there. So we got our thing. And if this two matches, that means the model got it correct. If somehow this two didn't match, then model got it wrong. Once we have this feature collection with these two properties, we can generate our confusion matrix. And let's call this test confusion matrix variable. And we'll take our validation data. And there's a function called error matrix, where we can give these two properties and we'll generate the matrix between those two. And you can see this was the confusion matrix that got generated. All the stuff in the diagonals is what it was correct. You can see this particular model has a lot more confusion in class 1, where there were 8 points which were we labeled as bad, but it got classified as urban. And this gives you some sense of which classes might need improvement. Once you have this, when you run this, you'll see that when it prints it, its object that you get out of this error matrix is an object called e.confusion matrix. I can go to e-confusion matrix. These are all the functions that I can run on this. So if I just want overall accuracy, I can call dot accuracy. And this will tell me from the confusion matrix how many samples were correctly classified and how many were wrong. And now you can say that 94% of the samples were classified correctly. So my overall accuracy of this classification is 94%. And now we have a numeric measure of how good is our classification. So now if we go and change something, we add more samples or we change the model, if this number goes up, that means whatever we've done is helping the classification. If it goes down, that means it's not helping at all. Always use this number along with a visual assessment. So this is a quantitative assessment. Always do a qualitative assessment as well. Always visually look at your result. See if the region that you're familiar with is classified correctly, because it is easy to obsess over this number. There are many people who say, I'll try to get this number as high as possible. And they'll do all the tweaks in the code to get this number. But again, remember what this number is testing. This number is saying that 94% of only this 200 pixels were classified correctly. You are able to validate only this 200 pixels. There may be other pixels, other regions, which are getting really bad because of what you're doing. And you may not capture that, because we have that label data only for those 200 pixels, and we are only able to validate that. So this doesn't give you the full picture of accuracy, it just gives you a partial picture. So again, always when you're working on a project, if you get something about 90%, that's great. Do visual assessment, see things that you can improve, but do not obsess over this number, because it's only giving you a partial picture of how those 200 samples have performed in your classification. But it's a useful number to have. It enables us to do a lot more analysis automatically and a lot more refinements automatically. And that's why having a metric is quite helpful. As we learned, there are many other metrics that you can compute. We computed the overall accuracy. There is something called producer's accuracy, which what remote sensing people call producer's accuracy. Machine learning people call it recall. So we can compute that as well. We can also compute something called precision, which is known as consumer's accuracy. And there's something called kappa coefficient. Again, this is not widely used nowadays. There's also something called F1 score, which is the average of precision and recall. We can compute this in Earth Engine. Let's do an exercise where you get to compute all of these metrics for the classification. Then you can explain the exercise.
So for the exercise here, we have the classification, and you see this is the full code for classification, and this is our classifier and classified output. Then we are doing the accuracy assessment, and here we have this test accuracy, and then we are getting the confusion matrix. So you see this is the confusion matrix, and this is the overall accuracy. Now your exercise is to calculate producer's accuracy, consumer's accuracy, and F1 score. So these all are inbuilt function in Google Earth Engine, and you can apply this on confusion matrix. So this is our confusion matrix. So you will be applying these function over there. Just in documentation, under the confusion matrix, you will find all these consumer accuracy and kappa and producer accuracy. So we want these three, just apply it on this and you will get the results. Just print it and see how it looks.
Let's do exercise 2C. Here, we don't need to change the region. You're not going to do this on your own samples because you don't have as many samples. Many of you would have just collected 10 samples for your classification. That's not enough to do an accuracy assessment. For now, just use the same setup. All you need to do is update this to compute this different metrics on the same data set and same region that we have selected. So see if you can figure out the right functions and print those numbers for this. Let's do exercise 2C in module 3. We learned about the holdout method for accuracy assessment, where we had our training samples. We split them into two parts. We used the first part for training the model and the second part for validating. And we got a number. Now, this kind of setup is okay, but what if when we split our data, even randomly, we got a very favorable portion of samples for validation? Let's say there were samples which were very difficult to classify and some were really, really easy. The easy ones went into our validation sample. And when we checked the accuracy was like, oh, you have 95% accuracy. So how do we ensure that whatever we're getting is just not matter of luck? So there is a variation of the holdout method, which is called k-fold cross-validation. So to avoid this effect of randomness on your final output, you again do this multiple times. You say, instead of doing this one time, I'll do the same setup 10 different times by taking each different subset each time, and then I'll get the average. And that means I can be more sure that the result I got is not matter of luck, but actually the performance of the model. The K comes from the fact that you are dividing your samples into K parts and then using some parts for training and some parts for validation. Let's visually see the results. So let's say we have all the samples. We divide into K subsets. So if you're doing a 10-fold sample, then you say divide this into 10 samples. In the first iteration, you take the first fold that you have, keep it for validation, train the model with remaining 9 folds. So let's say you had 100 samples, you would split this into 10 samples each. In the first iteration, take the 90 samples, train the model, check the accuracy with the remaining 10 samples. In the next iteration, take the second fold as your holdout, train the model with the remaining folds, check the accuracy with this. And that means you do this 10 times. Each time you're testing accuracy against a different subset. That means even if one subset was favorable, you will average out those variations. And then finally, you just take average of those, and that'll be your final accuracy. Many people would want to do this for their actual research work or when you want to check the model's performance. We have a script available in our supplement folder, which I'm going to show you. So here we can do this n times. I think in practice, typically you do a 10K fold. So K fold, usually K is 10, but you can do less or more depending on what you want. Let's see the script. We have the supplement folder where we have organized scripts in different folders. I'm going to show you the one for the K-fold validation. So here's a supplement folder. There are many, many scripts inside. I'm going to look at the supervised classification folder and open up the K-fold cross-validation script. Here is the implementation. We have this function called K-fold split, where you take your GCPs and use whatever K value that you have. The way the function works is it takes whatever K value given, divide this into K steps, and then for each of those, it'll assign the random values, split that randomly into the folds for training and validation, and train the model. Will first give you those splits, and then you go and train the model for each of those. And again, we are using MapReduce to run this multiple times. We're not using a for loop. So we say for each of the fold, map a function, which will take this fold and do your training of the model. You'll training the model and checking the accuracy of those. You can pick any metric for accuracy. Here we are using the overall accuracy as the metric. And if we did this 10 times, you can see that we're getting different accuracies. You can see one of the folds gave 96%, one fold gave 92%. But if we average out, the accuracy is 94.5, which is a more representative of the actual accuracy. So if you want to implement this, you can just copy paste the code. The way we have structured the code is they are very easy to copy paste. So if you want to try this on your own data, you should be able to copy paste this. And as long as you have a variable called GCPs and an image called composite, things will work. We've been working on our supervised classification implementation. We started with collecting training samples. We use visual interpretation and looked at the images and dropped some points on different land cover classes. We collected the data, we trained a classifier, used a random forest model to and trained this with the collected data. And then we applied that model on unknown pixels to classify the image, and we ended up with a classified image. To assess how good is our classification, we also did accuracy assessment, where we took some of our training data and held it back to test the performance of the model against. Now we have a good measure of the accuracy, and the natural question for a lot of you would be, now how do I improve it? I have some measure of accuracy. What if my model is not performing well? What are the different things I can do to improve the accuracy? One of the first things we have to do is something called feature engineering. So far, we've only used the bands of a Sentinel-2 image as an input to the model. So we told our model that here are the 12 bands, and we have the reflectance at each pixel. We have trained a model to learn from those reflectance values and predict a class. Now, the model can pick up the relationship between those spectral bands and the class, but we can help the model by either transforming these features into indices. So for example, we know that if you want to predict something that is vegetation, NDVI is much more easy to a direct correlation to a vegetation class rather than the raw bands. So if we can transform our input data into ratios, maybe the model will learn better. Also, we'll see that sometimes there is other information that is not in your satellite image, but there's other information that can help the model learn better. So we can add all of this information to our model, improve the feature space that it's learning from, and it should help improve our accuracy. This whole process is called feature engineering, and we'll see how to implement this in Earth Engine. Let's dive into the code. Here we are. We're going to start working on script 3A. This is what we've done so far. We have our training samples, and we have this region that we want to classify. So we did our training and validation split. We did 60% samples for training, trained our model with it, and then tested the performance with the validation fraction. And we have about 94% accuracy. And you can see there is some confusion with the bear and urban class here. So our idea is, can we improve this accuracy? Also, as I mentioned, do not obsess over this number. You also should visually check the results, do a qualitative assessment, and see how the classification is improving. Also, just a caveat that we are already at a very high accuracy. Typically, at large scales, remote sensing machine learning models do not give you such high accuracy. So again, we have limited room to improve, but there's still things that we can do to help the model. So right now, look at the training feature that we've been using. So if you look at the training samples, we have taken a composite image, which had this 12 bands. And when we took our sample points and we extracted the pixel values, we got those 12 values as a training feature. So the model is learning from this feature where we have this 12 values, which is the input, and the model has to predict the correct class based on that. Let's help the model. We can improve our feature space by adding different indices. The way you do feature engineering with remote sensing data is we have our composite image, which has got this 12 bands. If we add a new band to this image, that means when we sample that, our feature will get that column. So when you think of adding new features that your model can learn from, think about what bands can we add to this composite image. This is usually very hard in a remote sensor because if you want to add a new band to an image, traditional data formats will say, oh, if you want to add a new band, it has to be the same data type, same projection, same pixel size, and all of those restrictions. So whatever data you want to add, you want to first do this pre-processing. Earth Engine says, doesn't matter. You can have even each band can be in different projection, different pixel size. It can be from a totally different data source. When you sample that, that's where we specify the resolution and the projection, and everything will get resampled and reprojected. So Earth Engine's data model is uniquely suited for this kind of machine learning work. Let's see how we can improve the feature. I'm going to comment out this part of the code. Right now, we're just going to look at our training features. So we have our composite image, the 12 bands, and we have our training features. How can we improve it? Well, we have our composite here. We can first add some indices, compute some indices based on these bands, and add them to our composite image. As we add new bands, our training features will get those features. Let me write a function. So here is a function where we have this input image with 12 bands, and we can compute different indices. Typically, I like to add one index per class that we're trying to predict. There are indices that are useful in determining different classes. So we have a vegetation class, NDVI will help with that. NDBI is a built-up index, will help with the built features. NDWI will help with the water features. And then there's a new index we've not seen before. We have a bare class. So there is an index, this specific design to accentuate the bare soil. And this is called a bare soil index. We've implemented this for, and again, we don't need to know which of this is actually useful. If you think of another index, feel free to just add that to your model. That's the beauty of machine learning. You don't need to guess. The machine learning model will figure out if it's useful, if it's helping the model perform better by using the NDVI values, it'll just use those. If it doesn't help, it's going to ignore that. Right? So again, it takes us the guesswork out of what features might be important, what things I should do, what should be the threshold. Nothing. All you do is you just throw more data at the model, and the model will figure it out. We'll also see once the model is trained, you can actually see which features were useful to the model. So you'll also get that feedback. Say that you added this band, but the model didn't find it useful. So again, that's a good feedback loop that you can use. So here's a function. Let's just add it to the image. Here we have this composite variable. One useful tip when you're setting this up is you can reuse the variable name. So I can say, I want to run this function. And give the composite image as input. And then when it returns, typically you will say composite with indices or something. If you do that, you'll have to change all the variable names in a script. You can overwrite the variable name. You can say now my composite is this one with the bands that have been added. So this one line will just say, okay, now I have this extra 4 bands in my image. You can see my composite now has 16 bands. And when we go and sample this composite image with 16 bands, you'll see that our training feature will also have this new features. Instead of just 12 values to learn from, it has now 16 values to learn from and predict class 0. So we just added 4 new columns to our training table. So the feature engineering becomes a process of adding new bands to your composite. And then once I uncomment everything, the model just learn from it and then use that in your prediction. Here you'll see that this is line cover 0 is urban, and you can see the NDPI values are high here. And again, we don't need to know that a priori. The model will figure out that if this is more useful than the raw spectral bands, it'll use that. What else can we do? Another thing that might be helpful is we can say, let's add some other data. Depending on the class that you're trying to predict, there may be things that may affect the output class. One of them might be, say, slope and elevation. Maybe there is a relation between pixels which are at higher elevation and certain vegetation. Let's say you're trying to map coffee, maybe coffee grows at higher elevation. And so if there are 2 pixels with similar values, how does the classifier separate them? Maybe the one with the higher elevation is coffee. Similar to things, if there is a pixel, 2 pixels with the same values, but one is on high slope and one is on low slope. And if it's high slope pixel, likely that there is no built up there. So maybe there is some relation that the classifier can use to separate out pixels which have similar values in other bands, but this band has unique values. It may or may not be useful, but again, we say, let's try it out. I have the model learn from slope and elevation as well. Again, doing this with the traditional methods, you'll have to first find some elevation data, download it, mosaic it, reproject it, resample it to the same projection. Then you can add it, and then you can start using it. In Earth Engine, all you do is you can say, I want some elevation data. So you go and say, I want some elevation data. There are literally hundreds of local, regional, and global elevation models available. You can go and pick up any one that suits your needs, and you can start using it. The one that we're going to use is elevation data called ELOS DSM. This is slightly better than SRTM. SRTM is the gold standard, but it's 25 years old at this point. So it's very, very old data. This one is slightly newer, and it's a good 30-meter resolution global elevation model. So you can use this. If you are in a region which has got high resolution, newer elevation model, maybe you can use that as well. So let's just use this data. I have some code. I'm going to just copy paste it here. The elevation data has a band called DSM, which is the height of each pixel. If you want to compute slope, there is the function ee.terrain.slope, which will take an elevation model and then compute the slope. So now we have these 2 images. One is an image where each pixel value is the elevation of the pixel. This pixel is the slope of the pixel. And now I say I want to use that in my machine learning model. So I'll just say I'll overwrite my composite variable and say my composite is this composite with the 16 bands, plus add this new band of elevation. We'll also add the slope band. And now you can see my composite has 18 bands. So I have spectral bands. I added these 4 indices and now have elevation and slope. So now when I go and sample that composite to build my model, my training feature will now have slope and elevation at each pixel. And this will be different for each feature because we are extracting the value at the pixel. And now the job of my model is to say, I have all of this input. Can I use this to predict the line cover class 0? And then for other feature, it'll be a different set of values and say, can I predict line cover class 1? So now there's a lot more information that the model has, and maybe it'll help it separate out some of those confusing classes a bit better. We can keep going. For example, if you say, I want to add some temperature data, you might say there's a newer building, there's a canopy data that just came out. Maybe we should add that. You can keep adding different bands to it, and the model will just keep learning from it. Let's see what does it do to our model. I'm going to uncomment the remaining code. We had started with like a 94% accuracy. it improved slightly, 95%. You can see there was 8 points which were classified as wrongly classified as urban. So that removed some of that confusion here. We didn't change our training data. All we did was just give more information to the model. And you can see the results. If you visually compare the before and after, you should see some improvement in some of the classes where the model would have picked up some of those information from the additional band. Once we have done our feature engineering, we can actually check what features were helpful to the model to learn and predict the class. Once you train a classifier, so here we have initialized a classifier and trained with this training data. Many classifiers have these properties where you can kind of look inside the classifier and see some results of the training. So we can use this function called .explain, which will tell you a little bit more about the training process. This function is available for most functions, not all of them. So if you're using certain classifier and you say .explain, it won't be available. Here is the result of the classifier.explain. It says the classifier was trained to predict these 4 classes. Number of trees were here. There is this importance. If I expand this, this says when we used all of the features, which features were most important for the classifier. The higher the value, the more important the feature. So you can see in this kind of training, BSI was the most important feature. NDWI was important. The band 5 and band 7 were not that important. Slope and elevation didn't really help much. And so you can also use that as a feedback loop and say, maybe I added slope and elevation didn't really help the model, I can remove it. Because at some point, there'll be diminishing returns. And also, if you add too many of these input features, the performance will start to degrade. So typically, random forest models do well with 50, 100 features. As you start having 500 features, the performance will start to degrade. So you don't want to add too much information, which is all superfluous information. So you can also use this to kind of remove some of the features which are not important. Note that there is a degree of randomness to this. So if I change my number of trees, if I tweak some of the other things, this absolute values will change. Relatively, the values should give you a decent idea. So again, because these models are initialized randomly and then they are trained with this, you cannot expect the same distribution if you just tried on a different account or with a different randomness. But again, it'll give you an idea that definitely BSI is more important than elevation in this case. How much important, you can't really deterministically say that. Then here is the trees. So remember when we trained this 50 trees, this is the text representation of those trees. You can see this is the first tree. The way to read this is at the root, you have a split at band 11. It says first check the value of band 11. If it's less than 655, assign it class 3. If it's greater than 655, look at this and say if it's less than, check the band 2. If it's less than this, assign 3. If it's not, go and check NDVI and so on. So this is the representation of the tree. This is the first tree that was trained. This was the second tree, third tree, and so on. You can actually see all the trees that the random forest model trained. So this also is useful to understand what the trees were created. What are some of the other transformations that you can do for your data? I'm going to show you some scripts from our supplement that will help you improve your features and help the model learn. Open the supplement folder. Under the supervised classification, there is this script on image normalization and standardization. We noticed that you can see the different features at different magnitudes. So if we use it as it is, the models will get biased towards larger values. The good practice is to always have all the values of the same magnitude. So to do this, you can say, I will normalize my values. I'll take each band, compute its maximum and minimum, and make sure the values are between 0 and 1. So you'll take the value, subtract the minimum, divide by maximum minus minimum for that band. And all the bands would be transformed between 0 and 1. So the absolute values will change, but relatively, they'll have the same values. So for example, if the elevation of a pixel was 500 and the maximum elevation was 1000, it'll become 0.5. So the relatively, there'll be the same relationship, but then the absolute values will be transformed. So model will not be skewed to this. Here's the code for this. So here we have this function, which will take an image and normalize the values here. If I want to use this, I will just going to take this and show you how we can apply this to our data. I'm going to look at the completed script, and we'll say I want to transform this, and I have my training features. I want to change the magnitude of this. So we'll take our composite here, and we're going to normalize it. So we have this normalize function. We can just say now my composite is actually the normalized version of this. And you'll see this is quite a computationally intensive process because we'll compute the statistics on this particular region and then apply them on each pixel to transform the data. So it might take a minute to do this. To speed it up, I'm going to just do this at a lower resolution just to show you the result quickly and see that how the transformation works. This will kind of give you an approximate answer, but you'll see the transformation that happens here. You can see now my computation is finished, and you can see all the values are transformed to be between 0 and 1. And now the model would not be skewed towards larger magnitude, and generally the performance would improve on that. When you're trying to add all of this bands and computation to your model might give you errors like say timeout, or you might get this error saying that this is too large a computation. A fix for this is to actually export your data. You can cover that in the upcoming script, where as your process becomes more complex, Earth Engine cannot do this computation in real time. There's a limit of 5 minutes in the code editor, where if something can be done in 5 minutes, it'll say there is a timeout error. Please export this data. So we're going to export this data and we'll finish the time. Okay, let's do our exercise. I can explain.
Yeah. So for the exercise here, you see that we have this function which will help you add new features to the existing composite. So here we are calculating NDVI, NDBI, and other indices, and we are adding it to the composite here. And then we are having slope and elevation bands, and that also we are adding with the composite. So we are using this for training and training the classifier and classifying the image. So you are just going to take these lines of code and paste it in the first exercise that you did. So it was 1C for you, the basic supervised classification. I don't have any code over there, so I'm just showing you here. So you take that, we already have the classified image. We will have this code, and you will have another classified image which will have like the basic bands as well as the features. So you will see two classified images, and you can see the improvement using the feature engineering.
The idea for the exercise is to take the classification that you did for your region of interest in the script 1C and see how much you can improve by adding those features. The way the code is structured is that if you paste it at the end of a script, you'll get one more layer. So you'll have your existing classification that you did with just the spectral bands. We use the same training samples and now add the features. Check how the classification improves. For now, you won't have any accuracy measure because you didn't implement this in the script 1C. So just do a visual assessment. Check how if the classification improved. Are you seeing any improvement? What things that were bad, which are now better? So just kind of assess and see if the additional features have helped your model. Let's try exercise 3. So we did some feature engineering. A lot of remote sensing work involves around figuring out how to take your different input data and prepare it for machine learning models. Some of the things are much harder. For example, right now we are classifying an image, which is a composite image. So you're looking at a median pixel value and you want to try to classify something. Now, if there is an agriculture and there is forest, both will look green. Both will have similar spectral signatures. How do you separate them? The classifier cannot separate them out. You can just say this is vegetation. Now, if you want to do crop classification, you'll have to say, oh, I need to figure out a way to encode the whole time series so that if the values have changed over the years, that means it's likely agriculture. The values have stayed vegetation, that means it's likely a forest. Now, how do you take this time series data and aggregate and transform it into a tabular format that we need? You have to be able to do things like time series modeling. You take an NDVI time series, apply a model, get the model parameters, and use that as input to your images so you can encode some values. People also would do seasonal composite. They would say, I would have some bands from the dry season, some bands from the wet season, and add all of that as input features. And that will have some differences between what was agriculture and what was forest. So you have to kind of do all of these things to encode time series. Another problem with this kind of pixel-based classification is when you classify a pixel, the model has no notion of what is around the pixel. There are certain kind of classes which are very hard to classify just by looking at one pixel. Plantations are a classic example where there is a specific pattern. So there is, let's say there is a plantation where there is one row of vegetation with some gap and the next row of vegetation. Traditional pixel classifier will say vegetation bare, vegetation bare. Okay? It's not that. It's the whole thing is a plantation. How do you kind of let the model learn what are the surrounding values? So this, again, people had invented different techniques for this. So this was a big problem that people had to encounter with, where you have to kind of figure out how to take all of these different data sets, encode them, and use them as features for machine learning. Google recently attempted to solve this problem, and they released a new dataset called Satellite Embeddings. This dataset was produced by an AI model. This AI model is kind of the new age machine learning AI techniques that was pioneered by ChatGPT and large language models. So the way this large language models worked was using this thing called embeddings. And this model applied the same concept to satellite images and tried to produce a data set which can then be used for machine learning tasks. The idea for this model was that we'll try to learn from many, many different data sets. Each pixel is observed by so many sensors. And can we just take all of this data, fuse all of them together, and generate an embedding which can uniquely represent the pixel, both in space and time. And then that embeddings can then maybe later be used as a proxy for all your features that you can derive from those data sets. The unique thing about this data set is many other people had produced such models. So the model would say, feed me some data, I will predict and give you embeddings at those pixels. But then you had to run those models on GPUs, you have to download data and process it. Google said, let us run those models ourselves on all the data that we have, and then give you the output embeddings directly as a data set, which you can use in Earth Engine for doing your machine learning task. They have produced the embeddings for each year from 2017 to 2024 at 10-meter resolution. The primary dataset for this was Sentinel-2, so that means it's the same resolution as Sentinel-2, but they have added many other datasets. And the plan is to continue generating this in the future. So now if you have a task that you are to use between this time range, it is likely that you can skip all of the feature engineering and just use these embeddings as input features to your task. This is a image that Google produced showing kind of the concept behind the data set. There are satellites that are constantly capturing data over Earth. Not just one, there are many, many satellites that are capturing the data. They've captured data at different time periods during the year. And you take all of this, you feed all the data for 1 year to the model along with all the data from different sensors. And the model just produces 64 bands. So it produces only 64 values at each pixel, which uniquely represents the spatial and temporal trajectory of the pixel. So it learns from all the observations of the satellite at this location for a year. It also learns from the neighborhood. So it encodes what is around the pixel and then compresses all this information into 64 values, which uniquely describe that pixel. So what data source has this model learned from? It learned from Sentinel-2, but it also learned from other data like radar data. Radar data can capture unique things that optical data cannot do, things like the structure of the surface. Your crop might look green in both the pixels, but they have different heights. How do you measure that? So the radar data, the SAR data would capture that. You have different materials which will reflect the SAR light, scatter the SAR signal in a different way, so you can detect things with different materials. They also added Landsat 8. So imagine the input feature space is so big where you now have not just one image, it's not a composite image, it's just all Sentinel-2 images. Each Sentinel-2 image has those 13 bands, and maybe there are 20, 30 images for a location in each year. All of them, plus all the Sentinel-1 images, all the ScanSAR images, all the Landsat images, that becomes input to the model. In many tasks, you also want to incorporate the climate data. So if you want to know, trying to do crop classification, you want to know what was the response to rainfall. And then you can separate out rain-fed versus irrigated agriculture. You are also doing some studies, and maybe humidity and temperature is important. And you want to use that as your parameters for a model. So many people had to now go and learn from ERA 5 data or other climate data. So this dataset also includes ERA 5. Plus elevation data, we just saw elevation might be important. And they added a bunch of other data sets. Like there's a gravitational field data set, there is JEDI, LiDAR data sets, and so on. So this added a whole bunch of data set, all of the observations for a year. And what the model produced was just 64 values at each pixel. And those values will uniquely identify this pixel based on all of the input that it received through the year. This is the full list of the data that was used for training the model. And you can see this is the Sentinel-2, Landsat 8.9, Sentinel-1, ScanSAR, some DEMS, JEDI, ERA 5, and so on. So now, if you're thinking of doing feature engineering with any of this data set, you can just skip all of your feature engineering and just use the 64 bands features that the embedding dataset produces. This is available readily in Earth Engine. So you can just readily read the data. At each pixel, you'll have 64 values for each year. And you can say, now I want to use this to classify it. This kind of models are known as foundational models. When they were training the model, there was no specific purpose in mind. It was not trained for vegetation. It was not trained for urban classification. It was not trained for biomass. It is a general purpose model. That means there's no purpose. You are the one who decide what is the purpose. So you would say, I will now take this data and I will use it to train it to classify different land cover. You can also take it and use it for regression. You can also say, I'll go and find pixels which are similar and then do some similarity search. So you can kind of derive different use cases. Think of this as a replacement for all of this input data sets. Instead of doing the feature engineering and data fusion yourself, you can directly use this one. The great thing about this is those 64 values have encoded the full trajectories. That means if there is a pixel with a crop which grows in the summer and is harvested in winter, there's another pixel where the crop grows in winter and harvested in summer, they'll have different embeddings. Even though they might look green in this data set, they'll have different embeddings because they have different temporal trajectories. Same thing is it looks at the surrounding pixels, it looks at all the pixels in a 1 kilometer radius. So anything that you can say 2 pixels similar, but then surrounded by different things will have different embeddings. All the data set is cloud mask, gap filled. So again, all of the data set doesn't have any gaps. There's no clouds, no correction needed. You can just directly use that. You get one image per year with 64 bands, which can be later used for applications. Let's see how we can use this for a classification application and how it simplifies some of the workflow. This is, you are using an AI-derived dataset as input to a model. This kind of things are called fine-tuning. So you take your foundational model output and you take this general purpose embeddings and then fine-tune it to your purpose, which is the classification task. You can fine-tune it for different tasks as well. These are the different applications. We're going to focus on doing feature engineering for classification. Let's dive back into the code and then we'll see what this data set is. And start working on script 4a. This is the dataset in Earth Engine. It's called Satellite Embedding V1. This is an image collection. You have one image per year from 2017 to 2024. There are pixel size 10 meter, and then there are 64 bands. These are the 64 embeddings that were generated. One thing to note is each of these bands do not have any meaning to it. So do not even try to attach any meaning to it. There is no band for agriculture. There is no band for crops. There is no band for January, right? So there is no interpretation of these bands. All of the values should be used together. So whenever you're using the embeddings, the idea is you should always use the 64 values because they completely represent what the pixel is seeing. You cannot say, oh, I will only use the first 10 because I want to only do the first season. No, there is so much more information at the pixel that you cannot separate out what the models learn from that. So what we can do is we have this image and we want to classify it. We have created a Sentinel-2 composite just for visualization. We're not even going to use this composite image. This is just for our reference. What we want to do is we want to use the satellite embedding dataset, and we say load the collection. We filter it for the time period. So we're working on this 2019 classification. So we create a start and end date, and then filter all the embedding styles for this particular region, and then we create an embedding mosaic. So we just create a mosaic, and we say this is the mosaic that was created for this region. And again, we have 64 bands. There's no good way to visualize this data. So if you want to visualize this, you can say, maybe I can do some 3 bands at a time and try to visualize what the data is. But you can't see all of the data. So it's tricky to visualize. But if you want to really visualize, we can try. So let's say there is some code given in here, which we can try to visualize this. The embeddings are, the values are unit length. That means when you have the embeddings, they value, the length of the vector is 1. Typically, they range from -1 to +1. So again, the magnitude would be between -1 to +1. You can pick any 3 bands if you want to visualize it, and then we can just try to load this up. So we're looking at only the 3 dimensions of the 64 dimensions of the data. This is just useful to have something on the map so you can inspect it. But again, there is no way we can interpret this because there's so much more information here. Here is what embeddings look like. If I inspect a pixel, you'll see that this is what the embeddings look like. There are 64 values that have been created for that pixel for that year. Out of those thousands of bands from Sentinel-2, Sentinel-1, ScanSAR, ERA5, and all of that, right? So you can also see that there's a lot of precision to this. You can use the full precision because there's lots of information here. It's a very information-dense data, and you have all the information here. You can try visualizing different combinations of bands to see this, but again, visually, you cannot see the richness of information. There's a lot more information that you cannot simply see with just 3 bands. So once we have this image, we can say we have the 64 features that I want to use for classification. So we can train our classification model and say we have our GCPs. We'll split this into the same ratio that we've been using. We overlay this on embeddings image. Remember, we're not even using the Sentinel-2 composite. We're not using those bands. We said this already is encapsulated Sentinel-2, so we're not using that. We just take our embeddings image, sample our training features from that, and let's see what those training features look like. So now we have our land cover property that we had input to our labels, and now we have 65 properties. The 64 was the one that was extracted from the embedding at that particular pixel, and then we have land cover. So now our random forest model has to learn from the 64 values and predict this class 0. And if you have labeled your data correctly, the model will go and find what is the appropriate relation between different values that can allow it to predict class 0. And that's it. So you don't have to do any time series modeling, encoding for spatial context, no fusing of data. You can just use this embeddings as your starting point. Let's do classification. Now, so far we've been using random forest. Random forest is great. It can model a lot of the nonlinear relationships in your data, and it's robust against a lot of the overfitting problems. But for embeddings, the way embeddings work, there is a classifier that is preferred over random forest, and that is the KNN classifier. Let's look at the documentation. This is a KNN classifier, where the way to think about embeddings is you have the 64 values. And if you think of that as a vector, so think of this vector from 0, 0 to this coordinates in a 64 dimensional space. Now, if you have a similar pixel somewhere, they will have embeddings which are very close to that vector in that 64 dimensional space. And that means if there's a similar feature, similar land cover, they'll all have embeddings vector which are in the same region in that 64 dimensional space. If the pixel is something else, the embeddings will be pointing to somewhere else. So if you treat embeddings as a vector, and you can now start to partition that space into groups and say everything that is here is water, everything that is there is vegetation, and so on. There's a classifier called KNN, which is great at partitioning n-dimensional space into different regions, which is the KNN classifier. So KNN classifier is the preferred classifier to work with embeddings because they can be easily partitioned into different spaces that can model and cover. You are also welcome to use random forest. Feel free to try both. Talking to many people, I've been also testing this data set on many different things. If my current understanding is if your label data is very clean, that means you have good, clean labels where you have painstakingly curated the data and you don't have mistakes in your training data, KNN classifier does a really good job. But if you have errors in your training samples, then a forest works much better. So again, that's my current understanding. But let's train a KNN classifier and see what it does. We'll do E classifier, smile KNN, and we don't need to give any parameters. We'll just train it with the features. So we have our training features, which is this features, which is all the 64 inputs and 1 output. So we have our training features. The class property that the model has to predict is the land cover. And the input properties are all the bands. And again, we can kind of have the same thing where we can, instead of typing those 64 values, we can just say, look at the band names from this. Since we sampled this image, those will be the same as the band names. And now once the classifier is trained, let's go and classify our image. What image are we classifying? We're classifying this embeddings image. So the model is learned to take 64 values and predict those class. We say now take all those unknown values in this 64 band image and classify this with the trained classifier. And let's visualize this. We'll use the same visualization parameter that we've been using and see how it works. We'll also do the accuracy assessment. So remember, we were at 94% accuracy with the regular Sentinel-2 based classification. Now with the classification based on embeddings, we are much closer. You can see a lot of the confusion between the bare and urban is gone. If you visually see this data, the results are astonishingly good because what this model has is there's so much of information that it has that it can correctly predict the class even with this very little training samples. You also see that the results will be very smoother because there's a spatial context. Each pixel is looking at the surrounding, so there is less salt pepper noise because if there are two pixels side by side, they're likely to be classified in the same class because it can see what's around it. So you'll see that the results are much more smoother than this pixel-based classifiers. Typically in a pixel-based classifier, we have to do post-processing. In this embedding-based classifier, you don't need this because again, you are working with an output of a deep learning model which has learned from spatial context. This dataset is quite exciting is because for the first time, a very capable AI model is accessible to practitioners without doing any AI. You are actually doing very sophisticated AI, but you're just using the output of an AI model and applying it, fine-tuning it to your purpose, which you can now say, I don't need to deal with all the data processing. I don't need to do all the feature engineering. All of that is done by AI. I'll apply my expert knowledge. I'll apply this to my domain knowledge and then fine-tune it for my application. Before we dive into exercise, I want to share some resources. I spent last couple of years working on this data set. I was one of the trusted testers and collaborated with the DeepMind team who created this model and worked on testing some of the iterations. And my job as part of this project was to figure out what are the problems that you can use this data in the remote sensing domain and how to apply them to different problems and solve them. So I ended up creating this 5 different tutorials that step-by-step guides on applying this embeddings dataset to different problems in the remote sensing space. One, there are a lot of really nice applications on unsupervised classification. This tutorial will show you how to do crop classifications with this embeddings dataset. These are published in the Earth Engine user guide. These were created by me and as part of this project. And you can see it got step-by-step guide on how to use this clustering methods to do a crop classification. And again, because this whole time series is encoded, you don't need to do anything. You just use those 64 lines and do your clustering application. There are some interesting applications which you cannot do before. Things like similarity search. This is a really fun tutorial. You can try and detect many different objects. Typically, when you wanted to detect objects from satellite imagery, you have to go and build a custom object detection model. And that was much harder. Now, because each pixel has encoded everything that's going on in that pixel, you can actually take and find similar pixels and say, I have this pixel which has a specific things, like it's got, let's say, a tennis court. I want to go and find other pixels which are the same embedding. So go and find other things, and you go and find all tennis courts. You can find all golf courses. The example I took was, can we find all grain silos? This is a structure to store grain. This is a kind of cylindrical structure in middle of farmland. You drop one point and say, here is a grain silo that I can see. Go and find pixels in the Satellite embedding which have similar embeddings. And you go and find all the grain silos in the region. Just apply this and you'll just go and find all of them. And just goes and finds everything. Right, so this is kind of a classic similarity search that you can do with embeddings. And now you can do this using geospatial data. We've learned about how this data set can be used for classification. Let's do an exercise where you get to test it and see how it improves your own classification. Vigna, you can explain the next exercise.
Yeah, so this is the similar exercise to what we did last time in 3C. So for this 4C, we have embeddings data, and then we are going to use this to train the classifier, and then we are applying KNN for classification, and we will get the classified output. So again, we will do the same thing. We will take this lines of code, and in your 1C, the basic supervised classification that you did, we will go there and just paste it below. So you will have both the classified outputs, one which uses embeddings and one which only use the bands of the Sentinel. So here you will have 2 images as output, and you can just visualize the change.
So the idea here is you'll take this code, which will add the satellite embedding based classifier. You can add it to your 1C exercise, which you did, or you can even add it to the previous exercise where you have your base classification, the one with the additional indices and elevation dataset. You can add that code to your previous exercise and see what further improvements you get by leveraging the embeddings. So try this out. And I highly encourage you to go and now visually inspect the result. The things that you'll notice, one is the results are much more smoother. So there is a lot less salt-paper noise. You may lose some finer details. So again, watch out for that. See if you are losing any details that you want to keep. And those are the cases where the embeddings may not be useful because it has got the spatial context. See what mistakes were able to be corrected by the embeddings dataset, and generally what are the kind of improvements you see on qualitative level. So let's try exercise 4C and try this on your own. Okay, so we've done a classification. Maybe you use some features you did, or maybe you satellite embeddings, or maybe you did some normalization and have a very complex workflow. One of the things that you will find is as your script gets more and more complex, Earth Engine needs more time to process. Even with all the massive computation infrastructure, it needs more time to process. And as you start increasing the computation that you need to do, and when you try to print something or try to visualize this thing, you will get this error, computation timed out. Now, this error says that Earth Engine cannot do this in this environment. The code editor environment is an interactive environment. So they've imposed a limit of 5 minutes. So whatever you hit run, and if a computation cannot be finished in 5 minutes, it'll stop. It says, this is not the right environment for you. If you want to see the results of this, you have to use the batch processing environment. then that environment has much longer limits, much more resources, and you can run your computation for as long as you like. That system can be accessed using export. So we're going to learn about how to deal with large classifications, how to do large scale data processing, and export our results instead of visualizing them. And this is a two-step process. So if you want to visualize the results, but you can't really see this on the screen, it's timing out, you first export it. Once export is done, you import it and then visualize it. And the export may then be run for 10 minutes, 15 minutes, 10 hours, whatever time it takes. Okay, let's learn how to export data. We've learned how to export images as GeoTIFF files. We've learned how to export tabular data as CSV files. But let's say we are trying to export some data, which is neither an image nor a feature collection. So let's say I'm trying to compute accuracy of some data. So I have this confusion matrix and I'm trying to print this. I have a large classification and maybe this matrix itself is not printing. It's timing out because I've been doing something very complex and it just takes a long time to do it. How do I then export my confusion matrix? Maybe I'm trying to print the accuracy. So if I just say, give me the accuracy number, and I want to know what is the accuracy of my classification. And when I'm printing this number, maybe the number itself is timing out. It's saying, oh, you have to export this. So let's say we are trying to print this number. And if I'm doing something very complex, this number itself will say computation time down. How do I export this number? So let's learn another technique of exporting arbitrary data or arbitrary numbers. The trick here is whatever thing that you want to export, we can save it in a variable. And so now I want to export this confusion matrix and the accuracy. The trick here is to convert any data to a feature collection. When you convert to feature collection, then we can export it. A feature collection is, what is the feature collection? It's a list of features. What's a feature? A feature is geometry plus some properties. And what's geometry plus properties is just geometry plus dictionary. So now if you just put this number in this dictionary, put this in a list, and put this in a feature collection, we can export this. Let's see how we can do this. We want to export this number. Let's say I want to export accuracy. So I'll create a feature collection. This is a feature collection. A feature collection is a list of features. So I'll do a list of features. Right now, we have an empty feature collection with an empty feature. Now, a feature needs two things. It needs a geometry and some properties. What's the geometry of this number? Well, nothing, right? So I can set this to null. So I have a feature with null geometry. What's the properties? Well, I can just define a dictionary saying that this is a key and this is the value. And now suddenly I have a feature collection. And now suddenly I have a feature collection with one feature containing one property with the number that I want to export. Again, when you're trying to print it, it may time out because it's too much. So don't even print it. You can just say, now I want to export this. And since we have a feature collection, we can use export table functions. So you can either export it to drive or asset, whatever you want. So let's just say I want to export to drive. So what collection you want to export? This is a feature collection. The file name that we want to export, we'll just say accuracy. The file format, it's a CSV by default, so you can keep that. And now I have an export function, which I can run, and it'll run as a background task. Once the export starts running, I can close Earth Engine. This export task can go on for a long time. I've done very large classification. For example, if you're trying to do this for an entire country, even the accuracy printing or computing accuracy might take an hour. It's fine. You can just let it run. And once it finishes, it'll go and do this. Maybe you are trying different models. Maybe you say, I want to compute accuracy of 10 different models. I have 10 different models here. You want to come do this 10 times. Again, export is the way to do this. You can see my export finished. I can open this in the drive. I'll have a CSV file that we just exported, and this will have just one row saying this is the accuracy and this is the number. This may seem like a hack, but this is the official recommendation. If you go to user guide and say, how do I export an accuracy? Or how do I export a number? This is the way to do it. If you want to now add the confusion matrix, the confusion matrix is an object of type EE confusion matrix. Now, if you try to export it, it'll say, I don't know how to represent this object as a text. It is like trying to export e.date. Like you can't export something which is an Earth Engine object. You need a text representation. So depending on the object, you have to convert to text. Here, the E confusion matrix has dot array, which will convert it to a text array, a list of numbers, which you can export. So if I want to now export this confusion matrix along with this, I would say my matrix is this matrix dot array. And now if I export this, let's name it with matrix. And now this will also be exported along with my data. So if you have a date and you want to export a date, that is dot format, which will convert to a string, and then you can export. So depending on the object that you want to export, convert it to a text representation, and then you can export them as CSVs. This one also finished. Let's see what this looks like. And you can see now I have my confusion matrix here. So if you want this matrix for a paper or for copy pasting somewhere, you can use that. Sometimes when you are even trying to visualize an image, you can say, I've classified my image. I would really want to see my classified image. But when you try to add it to the image, Earth Engine will complain that memory limit exceeded, tile error. It's not able to compute this tile because it's too much of computation required to compute one tile. It can't do this in 5 minutes. If you get those errors, well, you can export images as well. We already learned how to export images to Drive. You can use export image to Drive function, but then this is a problem. You export image to Drive, you have to upload it again to Earth Engine. So if you want to continue working with the data in Earth Engine, preferable method is to export it to an asset. Exporting anything to asset will put it back into your account as an asset. This asset is a pre-computed asset. That means you can just readily visualize that. And this is also a best practice when you have your very large classification or data analysis work, break it into different workflows. So you will say, I'm doing some pre-processing, doing cloud masking, adding those features. Once it's done, I'm extracting data, maybe export the training data, maybe export the classified image. If you say, I want to compute areas of classification, first export the classified image. Once it's exported, then you can readily do analysis on that. This also makes it very fast where you say, what I want to know is I want to know area of vegetation. And if you're running this whole script and trying to tweak, you'll wait 5 minutes every time you hit run. But if you have this pre-computed, you can now just get the results instantly. So let's learn how to export images as an asset. We'll try to export this image, the classified image. So we have our classified image that we want to export. So we have our classified image we want to export as an asset. Let's write the function export image. There is the toAsset function, control space to autocomplete. You're going to ask what image you want to export. So we'll say we want to export the classified image. Description will say I want to export the classified. Asset ID. When you export image to Drive as a GeoTIFF file, you get a GeoTIFF file, so you'll have a name. In Earth Engine, when you export it as an asset, it'll ask you what's your asset ID. So ID is the name of the asset in your asset folder. You can give just the name. So it's I'll just use classified. If you just give a name like this, you'll just put it in your asset folder as the name. So you'll just get a new asset called classified. If you're doing a lot of export, you may want to organize them in a more structure. So for example, I have different folders and I want to put this in this E2E folder, end-to-end Earth Engine folder. So I can say I want to put this in a specific path. So all of you will have your cloud asset root. If I just click this button, it'll show you that this is the path to your asset root. So this is your project root. And I say I want the full path to it. So I'll say this is my path that I want to export this. And from there, I want to now export this to a specific folder. So in the project, you have this assets folder. So the assets folder will be your asset root. Within that, you say, I want to export into this E folder. And in that, I want to export this in classified folder. So you can give the full path to it. Remember that when you run this, all of the folders must exist. So if you want to create a folder named G class, you first go and create a new folder. So you create a new folder. And once it exists, you can use that as your path. Okay, so this is our asset root. Generally, I like to have it more structured so that it's easy for you to construct this. So the way I do this, I have this export folder, and then I will have the name of the classification. So I say, this is what I want to call my export image, and then I'll construct the path from here. And now I'll say, this is my asset ID that you want to use. So instead of just hard coding it here, I'll put it here. And this means if I have a V2 of this, I can just say V2 and run this. I don't have to kind of change this every time. So this is my exported image path. The next parameter it's asking is pyramiding policy. Now this one is interesting. I mean, when you export the data to your drive, you will not be asked that. You say, I want to export this classified data at 10-meter resolution, and that's it. It'll just export that. If you export in Earth Engine, it's going to ask you for this. Let's learn what is this. I'm in the Earth Engine user guide. There is this article about scale here, which we have seen before, that in Earth Engine, you are able to visualize images at different resolutions. So when you input any data into Earth Engine asset, it says, this is the native resolution image. Along with that, it'll also store all the lower resolution versions of the same image. So if it's a 10-meter data, it'll store a 20-meter version, 40-meter version, 80-meter version, and so on. And these are stored along with an image. So next time you say, I want to visualize this image, but I'm zoomed out, it's going to not serve this whole image, it's going to serve you the low resolution version. These are called image pyramids. And this will be computed when you export the image as an asset or when you upload a new image to Earth Engine. That's why it's asking, how do I create those pyramids? The default pyramiding policy for all data is something called mean. That means if I want to create a 20-meter resolution version out of 10-meter, just take average of 4 pixels. You can change it to median if you want, or in case of our classified image, imagine you have 4 pixels, which is class 1, class 1, class 1, class 2. If you just have average, the average pixel value will become 1.25. You don't want 1.25, right? It's a classified image, it's a discrete data. So in case of discrete data like this, you say don't do mean, do mode. Mode is just the majority value. So to say if this 1, 1, 1, 2, the lower resolution would be 1. This is how it's aggregated. So when you're exporting classified data as an asset, you want to specify this, you can use mode. And again, this is only for visualization at lower resolution. If you the data at whatever scale you're exporting will be stored as it is. It won't be aggregated. Region, we always specify the region when we are exporting. So let's do the geometry. Scale, at what resolution we want to export. Let's do a 10-meter. CRS, if you want to export in a specific CRS, you can do that. Otherwise, we can skip this one. Max pixels. Earth Engine will stop your export at 10 million pixels. So we'll just set it to a very high number and we are done. So now when I run this, Earth Engine will create this export task and run this, and it's going to create a new asset into this asset folder in this EQA folder called classification embeddings. For now, I'm going to put this in my temp folder and run this. And now my export will start. It's going to compute the classification at 10-meter resolution for the whole region. And once it's done, it's going to appear in my asset folder. Once this is done, I can start a new script and just load this asset. And I'm just able to visualize this directly without having to compute this every time. And this will ensure that when you are doing large-scale work, you are able to avoid any timeout errors or user memory errors. Pro tip, if you are trying to work on large region, first test your script on a small region. So let's say your task is to classify entire Canada, or you are trying to predict something on an entire country of Myanmar. Do this for a small region first, test your script. Once it's done, split your region into some tiles. either by admin region, either by just a grid of 10,000 by 10,000 pixels, and then export each of the tiles separately. And that will ensure that, again, each tile can run in the background and you can do the processing. You are able to also start up to 3 tasks at once. So imagine you're saying, I want to compute classification for entire country. You have a single task, it takes 10 hours. But if you split into tiles, you can run 3 tasks at a time and your task will go much faster. Right? So split your data. We have a detailed blog post with tips on how to split your large exports into tiles with the code. I'm going to point to this post here. I'll point to this post on a blog on how to tile this. This is from a real project that we worked on. We wanted to export this entire country of Estonia. And again, takes a long time, but now if we can tile this and split each tile into a separate export, plus we choose our target projection, no data values, etc., and we can get this really nice tile export in the desired projection, and you can go much, much faster. So do check out this post if you're interested in working on large exports. Let's try running an export yourself. Vigna, you can explain the next exercise.
So here in your exercise 5C, you are going to export the classified image that you created in your 1C. So you can just take these lines of code for export and go to the exercise that you have done, and you can paste it, and you see that the classified image that we are classifying, the same we are trying to export with the path. Here you have to change the path. So remember that export folder, you can just go to your asset and see which folder you want to create. If there are any subfolders, you have to mention that. Here you see that it is under Vigna P, and that much you see. And if you create new folders or anything, it comes like this, and you can just go and see.
Also, so if whatever name you see, that will be your project name. So if for Vigna it says e-vignapi, she will replace this with projects/e-vignapi/assets. And then if she creates a subfolder, she'll replace e2e the subfolder. So this is what you need to replace in your path. And then once you run the export, it'll appear in that particular folder. So let's do the exercise 5C. The idea is you take this code, paste it into any of your previous exercises where you classified the image and export that. You need to change your export folder. Once the export task starts, it'll take a few minutes. In the next script, we're going to take the exported image and visualize this. We've learned how to classify the image and do the accuracy assessment. We also did feature engineering. We also learned how to export data if it's a very large classification. So we've implemented the whole workflow up to here. And what more can we do? How can we further improve our classification? The next step in a workflow would be to tune the parameters of the model itself. Whatever model that we have used, we remember when we chose random forest and we put 50 trees, I said, why 50? There's no specific reason. We'll go and tune that later. And now is the time. Now that we have completed our classification, we'd say, can we extract the best performance from this model? Can we find what's the ideal number of trees that we should use for this particular model to get the highest accuracy? So we'll learn how to do the hyperparameter tuning. This is the process in machine learning where you tweak your model parameters to make it learn better and perform better. This is not changing the data or the kind of features. All of them is the same. You just say how the model learns, I'm going to change that. So same data, same inputs, I'm going to just learn differently so that I can predict better when I classify the image. So what are some of the parameters you can tune? Well, in a random forest model, you can say, how many trees should I use? Well, we don't know. That answer really depends on your data, your particular structure, your distribution, etc. So the only way to find out is to try the whole search space. So you can say, what are the different values, different possible values of the trees that I can use? I'll try all of it and then find the one that works best, because there is no equation or theory that you can solve to find that. You just have to try and run this with different number of parameters and see which one works best. I love this slide from one of the courses. It says, if somebody told you that, how to do 1 + 1, and you said, just try everything and find whatever answer works, right? So again, this is what machine learning is. You just try a whole bunch of things and see which one works better. If you go to a machine learning conference, and you talk to somebody, say, why did you choose this model? Or why did you use these parameters? And they would say, well, we tried everything. This is the one that gave us the best result. The trick here is if you do this with code, then you can do this fast enough and you can do machine learning. So we're going to learn about this method called grid search, which involves finding all the range of possible values and then searching systematically across the whole space to find the optimal distribution. We'll see first how to do this. We had to learn about export first because this will involve so many different iterations of training the model that you cannot do this in real time. We have to export the results. And the idea is, let's build 500 different models with different parameters. And we'll pick the model that has the best accuracy for our data set. So we'll have to first figure out how to do this different models and then how to train them and how to validate them, etc. The code is in the supplement. Let's go and run that. So we'll go to our supplement folder under supervised classification. We have the hyperparameter tuning code. So here we are learning how to take our code that we already built. We first do our regular workflow. We train a single model and say we have our data. We already learned about how to see the feature importance. If you do classify.explain, you'll see the relative importance. We have some code here which normalizes that. And you can also see a nice chart like this, which will show you normalized thing. So these are percentages. So the band 2 in this case was 11% important, and so on. So you can kind of understand which features are important. But now if you want to tune some parameters, we can say, I want to now tune this parameter's number of trees. Let's first go to the random forest. So this is the classifier random forest that we are using. There are so many different parameters. The one that we have to give always is the number of trees. We had chosen a random number, but now we need to find the optimal trees for this. So let's try to tune that. We first define a list of all possible values. So our search space for the optimal number will be 10 trees up to 150 trees at the interval of 10. So we'll try 10, 20, 30, 40, 50, so on. So this is a list. We already learned how to use this sequence function. We map a function. So for each of the trees, we'll say for a given number of trees, this function will train a classifier with that number of trees, train it with the training data, and then test it with the validation data. So we have our test fraction, which is the validation data, and we get the error matrix and accuracy. Here we are using the overall accuracy as a measure. You can also use F score if you want it. So we say train a tree with 10 trees, train a model with 10 trees, and test the accuracy against the validation data. And whatever accuracy number is get, you return that. And you do this 15 times, you get results like this. How many trees are optimal for this model? So in this case, we would pick 20 trees. We already use 50, but now we can say, why waste so much of computation? We can just use 20. So now we found the ideal value for that parameter. This is usually the last step in your model. Don't do this while you're still kind of tweaking your feature space and trying different things. Once you're done saying, here are the features I'm using, here is the model I'm using, and then you can tune the parameter to get best performance with the least number of computation. Now you might be thinking, there are so many other parameters. Can I tune all of this? Typically, machine learning libraries like scikit-learn would have built-in functions where you can just say, there'll be a function saying that tune these parameters. And it'll go and do the same thing internally and give you these results. Earth Engine doesn't have that function built in. So we have implemented our own function, which is just a bunch of map reduce operations, where we just say, now we want to tune two parameters together. So let's say we want to try number of trees along with the bag fraction. Bag fraction is for each tree, what is the percentage of samples that we'll use for training. It can range from 10% to 90% at 10% in intervals. So the values, the parameter can be from 0 to 1. We'll say, let's try everything from 0.1, 0.2, all the way to 0.9. But now the best model might be 10 trees with 0.9, or it might be 50 trees with 0.4. We don't know. We have to test all the combinations of those. That's why it's a grid search. So think of this rows and columns. One row is number of trees, column is bag fraction. You go and find which combination will give you the best results. We just take the number of trees, map a function for each tree will map a function and try different back fractions and then just return the accuracy. This one is now we are training 15 times 10 models, so 150 models. It's going to take a while for it to give results. So we just export the results. When you run this, the export will be a feature collection. We just export this to Drive. I had done this export a little while back. So let's open this. Once you export it, you'll get a CSV file like this, that with the back fraction of 0.1 and number of trees, this is accuracy. You go and sort this column and say, what combination should I use to get the highest accuracy? And there'll be some combination, maybe 90 trees with 0.5 back fraction gives you the best result. And that's your optimal number of trees. And you replace those parameters in your model and you found the most optimal parameter. If you don't want to just manually do it, the code also kind of does this automatically, just sorts it by accuracy and picks the best model. And then you can export the optimal model with the final classification. So this is like the script will say, don't even look at it, just give me the search space. It'll tune the model, build a new classifier with those optimal parameters, classify the image, and export your final classification result. Again, do this at the end of your process saying, I'm done. I have 95% accuracy or 80% accuracy. Do this, you might end up with like 2 or 3% jump in the accuracy and you get the final classification. One more thing you can do when all of this tuning and iteration doesn't work, in many cases, if you do even the most sophisticated things, if you have bad training data, your performance will not improve. So if you did all of this and your performance is still not good, you would want to revisit the training data. Either you review your training samples, look for errors, or you collect more samples for the classes that are getting confused. Some tips, we have some code that is available. We'll go through this code first. Let's say when you do a confusion matrix, you have some samples which were misclassified. Can you know where those are? Where you're trying your different iterations, you say always this one sample gets misclassified. I want to know where that is. Maybe I took a wrong sample. I just want to remove that. So let's look at this script first. The script is in the supervised classification folder in the supplement, identify misclassified point. So here's a confusion matrix. Can I know where are these 8 points? Can I know where are these 3 points? And this is simpler than you think. What you test is apply a filter where the classified class is not the same as your land cover class. So say, take all the features and say, I have all my data, I have each point. This is the land cover class, this is the predicted class. If they are different, show me that. You can also say, show me all the classes where land cover was 1 and classification was 2. So we can identify a specific one. Here's the code for this. We say, filter for my validation data where the land cover is 0, but classification is not 0. So these are all points from urban which are misclassified. We can say, show me all the points where the classification and land cover are not equals. And these are all misclassified points. You can also style them. So for example, this is all the misclassified points. And you would go and look at this and say, oh, these are the points which are getting misclassified. You can go and review them. Maybe you would have taken this could delete them, or you could put them in a better place. In my experience, a lot of these points are either will be mistakes or will be at the location which are very hard. So for example, it might be at place which is a mixed pixel, and that's why it's getting confused. So remove the sample, give a clear pixel, which will be easy. Sometimes it just could be a genuine hard thing to classify that will be difficult. So again, you can go and look at this thing and say, oh, this is getting classified. We had put it as vegetation, it is getting classified as a water. And you can see this is actually a lake overgrown with vegetation. And we see vegetation, so we had dropped vegetation, but it's actually water. So again, this, depending on the season, this might be problematic. So we just said, this is not a good example. Maybe I'll just show this pixel instead, which is a vegetation. And so this helps you kind of clean up your training samples a little bit better. Another debugging script that you can use, which is in our supplement folder, is to plot the spectral signatures of each of the samples. We expect that if the samples are for a specific class, they'll follow the same pattern. If you have one wrong sample which has totally different signature, you can actually identify and debug those. Let's see an example of this. This is the spectral signature script. All the scripts are designed so that you can just copy paste the whole thing and put in your code, and you can see those charts. Here is the chart. So if you just take the average value, this is the kind of spectral signature we should see. Like a vegetation should follow this signature where the NR is high, red is low. If you look at all the vegetation pixels, you can see they follow the same pattern. Some of them followed slightly different pattern, but if there are mistakes in my data, one of them will just stand out. We'll just say this will be very different. So if you plot all of this and say, oh, my water has all kind of values all over the place. Maybe there are this data set with a very high NIR value. This could be one of the mistakes in my data. So it's not following the kind of signature of water. This might be those pixels I dropped on a vegetation by mistake because they have a high NIR and low red values. Okay, see, this is like a vegetation that might be over growing a lake. You would look at this and say, this is the ID. You can see the 000. This is the ID of that particular sample. You can just filter it by the ID and see which those are. So again, if none of the techniques are working for you, you can go and revisit your training samples with those debugging scripts to identify which ones might be having problems. Another option to improve your training samples is if your samples are consistently getting misclassified for a class, add more samples there. Show more, like you have a really difficult class, maybe you are trying to map flooded vegetation. Add a pixel and saying, oh, this was misclassified, drop a pixel, this is actually flooded vegetation, it's not water. So you can go and correct those mistakes. Again, make sure you take pure classes. Most of the mistakes that you'll see will be because you dropped a pixel on a mixed pixel. And the classifier is really confused, whether it's vegetation or water or vice versa. With embeddings, especially, if you have bad results, it is actually easier to just start from scratch rather than debugging your samples, because the requirement of label data is so less. You can just do a systematic review, just go and look at each thing, or just start from scratch. Let's go back to our classification. Hopefully all of our exports are done. My export also just finished. So let's visualize the resulting export. Let's work on script 6A. In the previous script, we had exported our classification result. The idea was if you're doing something very complex, it's best to break down your script into different parts, where first you do your model and let the model predict all the values. Export it. It may need more time to export it. And you can export them as an asset. Once the export is done, you can then visualize this and do further analysis. So we had kicked off an export. You can see my export finished here. It took 12 minutes, depending on the size and the region. It might have taken less or more for your region. Let's visualize this. So I had exported my data to this folder. So you can replace this with your folder where you had exported. Remember, I had exported this into a temp folder for my classification, and I don't have my composite. So now if my asset is available here in this path, and I run this, you should be able to then find this, and then we can visualize this. Now, once we have our image, we can do some analysis on this. What kind of things you can do? One thing we can do is we can extract a specific class. Let's say we are interested in visualizing urban areas. How do I visualize only urban areas? I have my classified image. Maybe my task for this goal, for this whole exercise, was to map the urban core of the city. So I just want to know what areas are classified as urban. How do I select those? Well, we know the class of each thing. So we have urban is class 0. So how do I select from my classified image? We want to select all the pixels which are class 0. We can use these functions like EQ, GT, and T. These are the Boolean operators that worked on pixel levels. So we can say EQ0. This will select all pixels from this image with this condition EQ. So it'll find all pixels which are 0. Wherever this condition matches, the output will be 1. Wherever this condition doesn't match, it'll be 0. So we can visualize on the map and say this will be the urban layer. The minimum and max will be 0 and 1. So this will be a binary image. And we can just say this is my urban data. So now I have my classification, and I can just visualize the pixels which are classified as urban. And you can see now I have this binary image, which is the urban footprint of my data. Similarly, if you want a different class, you can change this value to be the appropriate class, and you can see those pixels in your data. I highly recommend when you're working on a classification project, break down your script. The first script should just do your modeling, export the result. Once the results are done, import this and do your analysis on that. So if you want to compute areas or if you want to extract something, do that in the next script. This will really help you separate the workflow. You can also do this iteration much quicker. Now you have an image which you can then play around with and get the results much more quickly. Let's see if all of you are able to visualize your exported data. You can explain the next exercise.
So for the exercise 6C, here first you will get the exported classified image here from the asset. So you will have to change this folder to your folder and you will get the classified image. And then we want to extract the vegetation class from the image. So while classifying, it was class number 2. So value of land cover property for vegetation is 2. So you will use the equal to function here and you will say classified dot eq and we want the value 2. So classified dot eq in the bracket, it will be 2. So it will give you vegetation. It will be the binary image with 0 and 1 where all the 1 pixels are vegetation pixels. So you will be just adding it to the map with the value 0 and 1 and you can give say green palette because it is vegetation. So you can try this first, just change this. So you will get your classified image, which you just exported and then get the vegetation pixels out of it and display it on the map.
Let's try exercise 6C, where you will import your asset that is exported. Make sure your export task has finished. If it says running, this will not work because the asset is still not there. You can also go to your assets tab and verify that this asset exists. Sometimes your export will finish, but you will not see the asset here. If that's the case, there's a refresh button here. When you refresh this, just update the list. Sometimes it takes a minute or two for the list to update after the export is done. So if you do not see your asset here, make sure you refresh it. Also, if you are sharing this with anybody else, you have to update the sharing settings. So once the asset is exported, for example, this is my asset that was exported. If I click on the share button, by default, it'll be private only to me. You can see this is private only to me. I have to change it to anyone can read, and then it'll be available to everybody else. So make sure when you're sharing this with your colleague or posting about this, you always change the sharing setting. If you are just keeping it for yourself, it's fine. You can just have a private asset that is available only to you. We're done with our classification workflow. There's one more step remaining, which is post-processing of result. So in our workflow, we have done all of this. We've done accuracy assessment, we tuned parameters, we fixed our training sample. You did some iterations of this cycle and you said, now I'm done. I am happy with my results. You export your results and they look good. Lastly, you can optionally apply some post-processing. This is again dependent on the application of your data. If you want to then use this data for some purpose, which is for mapping, you would want to post-process and remove the noise. If you want to use this to identify individual pixels of certain class, you do not want to do post-processing. So again, this is an optional step. In some applications may require this, some may not. The reason you need to do post-processing is when you do a pixel-based classification where each pixel is classified independently of the neighboring pixels, because of small differences and noise in your data, the two adjacent pixels may be classified differently, even though they are very similar, because they have slightly different values in different reflectances in different bands because of noise, which may or may not be correct. So for example, if you're trying to classify a large water body, there is 100 pixels of water with 1 pixel of non-water in between. It's likely that the pixel is misclassified. So you want to go and fix those misclassifications. So this is also a smoothing process where you remove this high frequency noise, where there is lots of this isolated pixels or this pixels which are surrounded by other classes. You can replace them with the correct class. We can do one thing. We can just say, we'll first detect clusters of similar objects. So you do a unsupervised clustering where you say, I take my Sentinel-2 image, I'll find clusters of objects which are similar. So then you'll find, and the clustering methods are a little more robust against noise. So you'll say, oh, this whole patch is bare. and you'll get this whole patch of bare. Then you compare this against your classification and say, oh, everything is bare except this few pixels here. And then you say, if anything that is different than bare, replace it with bare. And you do this for every patch, and you can do this automatically. You can also do this other method where there is a function in Earth Engine called connected pixels, which will tell you how many pixels of the same class are connected to each pixel. And you say, if a pixel is connected to less than 10 pixels of the same class, replace it with the surrounding pixels. And this will remove this isolated noise. Typically, in most methods in remote sensing, we would do a pixel-based classification, and then you would post-process this using clustering. There is some people follow the opposite method where they first do the clustering, and then they do the supervised classification of clusters. So first you find groups of connected pixels, which are all similar. And then you say, I don't know what is this. I'll train a classifier to classify them. This method is known as object-based classification. So if you are thinking of doing this, we have code that shows how to do that as well. Let's learn about this using clusters. So you first detect objects, which are a group of homogeneous pixels using a clustering method. These are unsupervised methods. We'll just go and look at the spectral values of pixels and find similar pixels. Once you find those objects, you say, this is the same object, so all the class of that object should be similar. If there are any other misclassifications, you go and replace those. We'll review this here, but as I mentioned, here we start with pixel-based supervised classification and then post-process using unsupervised methods. If you do the opposite, that thing is known as object-based classification. We first detect objects and do the classification. Both gives you the similar result, but again, many people say, oh, I want to try object-based classification. You can read this reference here. Here's what the classification would do. This is our original classification. Notice that there are all these isolated pixels. So you can see there's an isolated pixel here. There are a few pixels here. If you just say, do the clustering and post processes, you'll get something like this. You can see this looks much cleaner. There's all this high frequency noise that is gone. Now, this is great for mapping, where you say, I want to map water bodies, I want to map urban areas. But if you can go and see if your classification is good, this particular pixel of vegetation is actually an island in the water body. So there may be correct classifications, which you are changing here, which may or may not be desirable. So again, depending on application, if you say, I want to detect isolated trees, this is great for that, right? You just find isolated trees here. So again, don't post-process if your goal is to detect those. But if your goal is to create maps or have classification that can be used for aggregate statistics, cleaning this up will be helpful. The connected pixel one is using this function called connected pixel count, where you find patches which are not connected to as many pixels, and then replace those patches with the majority class from the neighborhood. This is what the same results would if you process using this connected pixel count. You can see it's less aggressive. You can control what's the threshold for how many connected pixels you want to remove. And you can see you keep some of those high frequency noise, but removing those really isolated pixels, which are surrounded by a class of lots of connected pixels. This kind of post-processing is required for pixel-based classification. If you use embeddings, you'll already get something that looks something like this. Because embeddings already have the spatial context, you don't get that high frequency salt pepper noise. So if you use the embeddings for your classification, you don't need it. But if you use additional pixel-based methods, you can apply some cleanup of your data. Let's see the code for this. The code is in the supplement under our supervised classification folder. We have post-processing classification results. So we'll go through the code first and then we'll see the result. So first we have our Sentinel-2 image. This is not using embeddings because embeddings don't need post-processing. This one is just using your traditional pixel-based classifier. So we take our composite image and we do unsupervised clustering. We are using a segmentation algorithm called SNCC. This one has some parameters of how you want to detect objects. Once you have the clusters, you can say for each of the clusters, use user mode. That means for each cluster, look at the class of pixels, replace all the pixels with the class which is a majority of those. So if there are noises between the clusters, it'll get smoothed out. The second one is this connected pixel count. So you take your image and say, give me how many pixels this one is connected to. And once you have the connected pixel, you can say wherever the patch size is less than 25 pixels, replace it with the smooth version. So here we are having 25 pixel is the threshold for our thing. You can adjust it to see the results that you want. If you see the results here, you can see this, the original classification is there. If you do clustering, you can see some of this noise is gone. If you see this one using connected pixels, you can see only the small patches are gone. Right? It kind of keeps the overall structure of the classification. The clusters will actually detect objects, so you might see bigger changes if you're using this. For connected pixels, you'll see smaller number of changes where you can see some of this noise is replaced. One word of warning, this one particular function, connected pixel count, this function will count number of pixels. Now, how many pixels are connected to this pixel? Well, that depends on the zoom level. So if I viewing the results here, I am looking at pixels at 2 meters. So my pixel size is 2 meters here. And I say, give me the pixels, 10 pixels connected, it'll give me 20-meter neighborhood. But if I'm zoomed out, my pixel is now 40 meters in size. So it'll give me much bigger area. It'll give you different results. A big complaint of Earth Engine users is when they use the function unknowingly, you will say, oh, when I zoom in or out, my results change. Because of course, the pixels are bigger or smaller depending on the zoom in and out. So how do you see your final result? Well, just export. When you export this, you are specifying the resolution that you want to run your computation on. So this thing, you say, please export this as 10 meters. Now my pixel size is fixed. And when it's post-processed, it'll be using that pixel size as input. So when you're building a code, if you want to preview the result, make sure you zoom in at the 10-meter resolution and then see the results. This will be your final results. But just note that there are certain methods which are pixel-based. The most notorious one is this connected pixel count. The forum is littered with people getting really, really confused why your results change as you zoom in and out is because of this particular function. We have a question. We still have a few minutes. I'll answer the question and we'll end the class. Can you apply low-pass filter? So low-pass filter is the focal mean. So focal mean is the low-pass filter in our thinking. So yes, you can apply it. But remember, focal mean, radius of the kernel to use, units, if you set pixels, it'll change as you zoom in and out. So make sure you use units as meters if you want to fix results or export the result as a specific scale. But yeah, low-pass filter is a focal mean in our thinking. And also, if you want a specific kernel, so for example, there are different kernels for low pass. If you want to use a specific kernel, there is reduce neighborhood function, where you can give any kernel that you want. And you can define the kernel with different weights and different sizes. And there's a whole kernel module with you can have different kernels available. So if you have some code that you've done in other software, and you want to implement this, and you say, I'm using a Gaussian kernel of this size and this radius, you can implement this using the kernel Gaussian and apply this using the reduced neighborhood function. Let's start working on script 7a. We'll learn how to calculate area for both vectors and rasters. Computing area in Earth Engine is slightly complex. It requires you to know about map reduce and some other functions that you are all aware of now, so we can learn how to calculate area. Here, we had exported the classification images in the previous section. We are just using the exported image. So this is the classified image that we had created using the embeddings. And we have 4 class classification. We have urban, bare, vegetation, and water. And now that we have our classification, we can now start asking questions about it. And that's what the whole purpose, that we can now do some analysis on this data. We can say, tell me, what is the area of vegetation here? Tell me what is the percentage of this area is urbanized. If I have 2 versions of this, I can say, show me the changes in the surface water extent between these 2 images. So we can start asking those questions. Most of the questions will require to compute areas. So we've learned how to compute areas. Here we have this geometry, which is a polygon object. So if I just add it to the map, This is our polygon for the boundary that we had used. So this one is our polygon. And if we have polygons and we want to compute the area of that, that's actually simpler to do this. So let's say if I want to compute area of the polygon, we'll say geometry. You can take any geometry, and there is a function called area. There are some parameters they're both options, so we can skip those. So we can just call dot area, and we can get area of the polygon. You get an answer saying that the area of the polygon is this. Whenever you compute area in Earth Engine, the result is always in square meters. So whatever area you compute will always be in square meters. So this is the area in square meters. We can convert it. We can convert it to square kilometers. We can divide it by 1,000 times 1,000, which is 1 followed by 6 zeros. I can write that at 1e6. So if I do this, you'll get the square kilometers. So this is the area in square kilometers for that polygon. Simple enough, no big deal. But if you now export this polygon and open this in ArcGIS or QGIS, and you measure the area, you will get a different answer. The reason you get a different answer is because Earth Engine uses its own proprietary area calculation algorithm. It developed this algorithm for doing distributed area calculation. So it can chop up this polygon into small sections, have each machine compute area for the small section, and so on. So it had to come up with its own way of doing things to do this parallel computing of area. Or GIS software doesn't do that, and it uses standard area calculation. So how do we kind of try to match this? Who's right? Well, Earth Engine has its own way, your GIS software has its own way. But then when you're trying to implement something and say, I did this in R, I've got this answer, I want to implement the exact same thing in Earth Engine. How do you test if your code is buggy or your answer is incorrect? So it's good to have your answers match with what you've done in the traditional desktop software. If you want to do this, we can force Earth Engine to use a specific projection. So we can say, don't use Earth Engine's own method, reproject this to a specific projected CRS, and then use the planar calculation for doing the area computation. And if you take the same polygon, reproject this in your desktop software or Python or R, you will get the same answer. If you want to do this, you can fill this 2 parameters. Most of the geometry functions in Earth Engine will have this 2 parameters where it says, if you're doing this geometry operation, give me a projection that you want to work with. So we are doing this, we can give an EPSG code. This region is in the UTM zone 43 north. The UTM code for this, EPSG code for this is this. So we can do this in projection. When Earth Engine is doing reprojection, it says, I need a non-zero error margin so I can reproject it fast. Because you're doing this floating point operations, Earth Engine says, I can speed things up a lot if you give me non-zero error margin. You can give this as say 1, this is 1 meter. At this scale, 1 meter doesn't matter. If you're working on very small digit point precision, you can even give some 0.01. But again, you need non-zero error margin in meters for Earth Engine to do the reprojections. And now if I did this, you'll get a different answer. You can see I got a different answer. But this answer will match exactly with whatever your desktop GIS is. Okay, so my recommendation for you is if you're trying to migrate some code or implement something that you've done, do this first. And once you're confident that your code is working correctly, you can switch to a more accurate area calculation method. This is more scalable. The way it works internally is when you're reprojecting, you're always introducing the error. Imagine this area was not just this one polygon. Let's say it was a global polygon. Let's say you have a big polygon and you want to compute the area. There is no global projection that is suitable for area computation. You will have very large errors. Earth Engine says, doesn't matter, it'll chop this big polygon into small pieces. It'll create an equal area projection centered at each of those pieces, compute the area, and then sum this up. And this is much more accurate than just reprojecting. So Earth Engine's method is more accurate, and you can use it. But again, if you're working with a client or a stakeholder, you don't want to explain that to them. You say, look, this is what you implemented. It's the same thing in Earth Engine now. If you want more accurate answer, I'll switch to this method. So just remember that there are kind of two ways of doing things. That was the simple part. Now we come to the more complex part. And that's why I said, if you do this area calculation Earth Engine, it's not a very straightforward. So vector area, remember, specify projection if you want to force it in a particular projection. Otherwise, Earth Engine will use its own area calculation. There's a question around, do you have control of the size of the polygon G uses for this area calculation? No, it's all internal implementation. We don't have any documentation or control over how this area is computed internally. And this is another thing that, you may not be very comfortable using this because you don't really know what's going on under the hood. There has been some kind of explanations by the engineers in the forums. I've linked to those in the course material. So if you want to know more about what's the algorithm look like, it's not fully documented, but I've linked to some of those in the class materials here. So again, there's some stuff here. There is some forum link here where the Earth Engine engineers are discussing their implementation. So look here for some. I'm not going to open this. It's kind of very technical discussion, but you can kind of look at what the things go under the hood. So now we have learned how to compute the vector area. Let's say we want to work on the problem of our interest, which is we don't want polygon area. We want the area for this particular image, and we want to have area of different classes. So let's say we want to compute area of one of the classes. Let's take vegetation. So I'll say my vegetation is all pixels which are equivalent to 3. So this is a conditional operator which will check each pixel if it's 3 or not. If it matches, it'll be 1. If it not, 0. So it'll give you a binary image. Let's visualize this vegetation image. So here is our image of vegetation. Here's a binary image. We have pixels which are ones and zeros. So if you look at any pixels which was classified as class 3, that would be turned into class 1. So this is 1. Rest all pixels are 0. So we turn into a binary image. So now we have ones and zeros in the image, and we can calculate area of the class. It's a two-step process. So first we calculate area of each pixel, and then we sum all the pixel areas. Okay. Even your GIS software works like this. If you ask QGIS or ArcGIS to say, give me the area of all the pixels, it'll say, I'll count how many pixels are there for each class. I'll know the size of each pixel. I'll multiply this and do this. Calculating area of each pixel. What is the area of each pixel? Does anybody know? What would we use the area of each pixel here? There's one answer, 100 square meter. Anybody disagrees? Scale times scale. So if the scale is 10 meter, then is it 10 meters? So the question I should be asking is in what projection? If I use, let's say, a 10 meter pixel in EPSG 4326, lat long, I don't know a 10 meter where. So 10 meter at equator will be some degree wide. The same amount of degrees will be different amount of size as you go up the latitude. So a 1 kilometer pixel at equator will be much smaller at a higher latitude, right? Because your projection degrees are not consistent. So again, you have to deal with projection. So either you say first reproject it to a projected CRS and then compute the area. That's what the desktop software do. Again, if you want to compute the area of the forest for entire Africa or entire world, Earth Engine says, again, I can't reproject it to a global equal area projection because there's not a suitable one. So that's why Earth Engine says we have a better method where we have a function called eImage.pixelArea, which will go and compute the area of each pixel depending on its location. So given the projection, if you don't give the projection, it'll use the the ellipsoidal calculation, and it'll say for each pixel, I'll compute the exact area in square meters at the given scale. So you don't have to worry about what projection, what pixel size, and it will be accurate at the global scale. Okay? So this function is designed to help you compute the area of each pixel. The way you do this is you first create an area image where you take a binary image, like say the vegetation, and you multiply it with this function, eImage.pixelArea. This image pixel area will generate an image where the value of each pixel is the area of the pixel. And you multiply it with ones and zeros. Wherever you had vegetation, that pixel will become the area of the pixel. All other will become zero. So this is the first step. Output of this will be an image where the value of each pixel is the area of the vegetation pixel at that location. Okay, once we have the area of each pixel, we can sum it up. This one's easy. So we can just say area image, not reduced region. We use the EE reducer sum. We have a geometry, scale 10 meters. Right now we'll skip the CRS. If you do a CRS, Earth Engine will reproject the data and use that CRS for computation. And if I print the stats, it'll tell you the area of vegetation. Oh, sorry, I have a typo here. In reduced region, when we are trying to do this at 10 meters, you can see hit an error. You have too many pixels. Earth Engine will give this error because we didn't specify the max pixels. Whenever you encounter this error, make sure you set your max pixels to a high number so Earth Engine doesn't stop your computation. The output of reduced region is always a dictionary. You get one value per band. Since we have only one band, this is the area in square meters for that particular class. Let's extract this. I will say vegetation area. There's a function called getNumber, which can extract a key from a dictionary. So this is a dictionary. So we say my key is this. And once you have it, you can divide it by 1/6. So you can get area in square kilometers. So we have 2025 square kilometers of vegetation in this area. It's a bit convoluted process, but I hope you can appreciate the reason for setting up this way. So you can get this very accurate area computation at a global scale without really worrying about projections. Here we didn't specify projection, so Earth Engine did its best to estimate the actual area of pixels at different locations and sum all those up to give you the most accurate estimate. If we want to force it to use a specific projection, we can specify a CRS parameter. And you'll get a slightly different answer, but that will be forced into that particular projection. And you'll see some slight differences here. As your area becomes bigger, the differences will be more and more, because as you are reprojecting the data to a projected CRS, you're introducing more errors in your computation versus this method is a little more accurate. Right. Any questions on area computation? If the projection is not specified, does the Earth engine use local projection? No, it doesn't use the local projection. It uses its own area computation method, where it divides the date region into small tiles, computes the area of each pixel based on its ellipsoidal thing, and then sums it up. And it actually uses the kind of ellipsoidal math to figure out the area of each pixel. So it's not in a projected CRS, it's just saying on a surface of an ellipsoid for this size of a pixel, what would be the actual area? Okay, let's do the exercise.
Yeah. So for the exercise here, you see that we are trying to get to the exported classified image of yours, and then we are having this vegetation class. We are selecting equal to 3, so this is vegetation, and that way we are trying to get the area of both vegetation and the geometry, and then we want to calculate the percentage green cover and round it off to the 2 decimal points. So first, you just have to get your classified image. So here you will have to change the path and you will get the classified image. And then you will just calculate the area of green cover and then percentage of green cover. And this is the challenge. If you can try this, just round it off to 2 decimals and print it.
Let's do the exercise 7C. The idea here is you have 2 areas, the total area of the region, the area of vegetation. You divide them, you get the ratio. Multiply by 100, you get the percentage green cover. So try this first. This should be simple enough. Just some basic math. You see the functions in the e.number module to see how you can do the multiplication and division. Once you're able to do this, the challenge is to round off this number to 2 decimals. So if you print any number, get this long decimal values, can you round it off to 2 numbers? And see if you can discover a function in the documentation that can does this. So first do this one. Even if you do this, that's totally okay. But if you have time, you can try doing this one. Let's do the exercise 7C in module 3. So we are able to compute the area of a single class. What if you wanted to compute the area of all the classes? One option would be to just change this one by one, say class 0, and then you get class area of that class 1, class 2. This is okay, but again, this requires things to be done manually. What if you had like 30 classes? That becomes quite painful. And you might say, oh, you taught us how to do map reduce. We'll write a map function and run this in a loop. That's possible. But Earth Engine provides you with a much more built-in efficient way of computing area of different classes. That is a concept called a grouped reducer. So instead of now computing area for each class using a reducer, so you say I have this reducer sum. Similar to a group statistics, you can say, I want to now reduce region over this area, but this is not a binary image. You can give it a 4-class image and say, give me the sum for each unique class. And that means in a single operation, you're able to compute the area of each of the classes together. I want to show you the code for this in your supplement section. We have the supervised classification. In that, there is a calculating area by class code. And if you now do this, you'll see that now the code looks very similar, but there is a e-reducer sum, and then you're grouping by the classification. And this means you can directly compute area of each classes, and then there's some further code to create nice charts out of this. So you can go and create a bar chart of all the areas. You can also, if you wanted the percentage for each of this automatically, you can just create a pie chart, which will give you a nice pie chart with the percentage of each class. So we learned how to do this manually once, percentage for each of the class. or each class. But again, if you're doing this with a multi-class image like what you have, look at the code in a supplement which shows how to use a group reducer. And there's also an explanation link if you want to understand how group reducers work. We are done with our module 3. In module 3, we focused on doing machine learning. We focused on type of machine learning, which is a supervised learning approach. We applied this to a classification problem of land cover data, and we did multiple approaches. We started with the spectral bands, implemented accuracy assessment. We tried adding different features. Remember, in geospatial machine learning, when you want to add new features, since you are doing this at every pixel, you want to add bands of those features. And you can add different features for improving your model. We then also learned about embeddings, and for many tasks, embeddings provide great features for doing your downstream tasks. So we'll use this to do in classification. And finally, we learned about if you ever get errors of timeout errors or memory errors, the solution is to export your data, which can run in the batch computing environment, which has much higher limits and can run for a long time. Finally, we learned how to calculate areas. So if once your classification is ready, you can also do some analysis. You are ready to do your assignment 3 now. In assignment 3, your task is to do an extended version of the exercises that we did in module 3. You can pick a region of interest. Feel free to upload a shapefile of your city, so you can get the precise boundary. If not, you can just use a polygon. You can use supervised classification, take some training samples, implement classification, at least 2 or 4 class classifications that we did, but feel free to add more classes of interest depending on what is your interest and what kind of classes your city has. You can add other things as well. Preferences to use the satellite embedding, so you don't need too many samples. 20 to 30 samples are okay for each class. We need a little more because we'll do the accuracy assessment. So you implement your accuracy assessment, so maybe 60-40 or 70-30, and determine what is the accuracy of your classification. And once you're done, you can try adding different things to improve. So maybe try using different classifiers. We mentioned that the KNN works best with satellite embeddings, but you can also try a random forest and see how it performs. And again, this is an open-ended assignment. Even if you spend just 30 minutes doing a basic classification with accuracy assessment, that should be good enough for the assignment. But if you want to apply this and try different things, if you want to improve and kind of do a really nice classification. We have the same presentation for machine learning. So I want to start and teach you some of the advanced machine learning techniques specific to geospatial science. So when you are working with geospatial data, you want to apply those standard machine learning techniques, you are losing a lot of information. Traditional machine learning models were developed for tabular data. So if you have a table of data and you say I have some columns and I want to use certain columns as input, one column to predict, and each row will become my feature, and I can train a model that can predict the class based on that. And when we apply those models in geospatial data, what we're doing is we are essentially taking our pixels, turning them into a table and saying that these are the bands. Each band will become one column, and we are creating this table where we have some input columns and we are predicting the output column. This works, but we are missing 2 key aspects that sets the geospatial data apart. One is in geospatial data, we have spatial context. We understand that each pixel may be at a different place, and that is really important. Location really matters. If there are 2 pixels, one is closer to a road, one is far from a road, and you're trying to predict something, that distance to road matters. And how do you capture that? What if in your image there is a north-south pattern, and if you sample 2 points from north and south, and they have the same reflectance, the classifier cannot tell them apart. They said they both look the same to me. It might be helpful to add the latitude and longitude information to say, okay, those 2 are separate. I've labeled them differently. How can you separate them? Well, you can figure out if there's a information in the coordinates that will tell you whether this is now north-south or east-west pattern. So adding the spatial context to your model will really help the model understand the spatial context and improve the classification. How do you add spatial context? We are still stuck on a tabular model. Random forest, decision trees, SPM, all of this classifiers expect a table. So the main trick is turning the spatial context into a table. I'll teach you some of those techniques. One thing you can do is if you want the model to have information about the coordinate where the pixel was sampled from, you can use this function ee.image.pixel.lat, which will add 2 bands to your image. So let's say you have a composite image and you run this function, you'll get 2 new bands, latitude and longitude. And the value of each pixel will be the latitude and longitude of those pixels. So when you sample that point, it says, here are the reflectance, here is the latitude, longitude, and here is your output class. And now the model can learn from lat and long if there's information to learn from. If it doesn't matter, the model will say it's not important, it doesn't help me predict the class better, it'll just ignore that. But it'll help you capture that coordinates if it's important. Second, there's a function called distance, which allows you to compute distance to the nearest pixel in an image or the nearest feature in a feature collection. A classic example that would use this is, say, you are trying to predict house prices, or you're trying to predict urbanization. If your 2 pixels are labeled as urban, or 1 pixel is labeled urban, 1 pixel is not urban, and they have the similar reflectances, but 1 pixel is closer to a road, 1 pixel is really far from a road. The classifier will learn that the pixels that are really far from the road are less likely to be urban. Similarly, if you're trying to predict housing prices, distance to beach, for example, distance to school, those are important parameters. And Earth Engine has this function called distance that allows you to capture that information as bands. So again, in Earth Engine, whenever you want to use any of this thing, you need to turn your whatever parameter you want as a band. So you create a band where each pixel value is the distance to the nearest object. And you can use that information in your composite. Lastly, if you say I have a pixel and I really want to know what's going on around it. So if you have 2 pixels, same reflectance, but one is surrounded by high NDVI, one is surrounded by low NDVI, and you want to use this information to classify them separately. There's this function called neighborhood to bands. So essentially it'll take the neighboring pixels and turn them into bands. So when you sample them, you'll have information about the neighboring pixels along with the pixel value itself. We have a sample code that'll show you how to do all of this and improve your classification. Let's take a look at the script to understand how all of these functions work. In your end-to-end repository, we have the supplement folder. I'm going to show you the scripts from the supervised classification folder in the supplement. Here is the first script, adding spatial context. Let me just print the composite. Comment out stuff and then uncomment it one after the other. So this is the image we are starting with, 12 bands, Sentinel-2 composite. And you said, I just want to learn from that. So when you have your training samples and you sample your image, each feature will get those band values and say, these are our input, try to predict land cover. How do we add more spatial context to it? First, let's see if we can add on this function, e.imagePixel.lat. And you'll see that your composite once you run this function, your composite will have 2 new bands, latitude and longitude. And the value of those bands will be the lat and long of each pixel. So now when we sample that composite image, you see that each training sample has the band values plus latitude and longitude of that particular point. And now the classifier can learn from that. Right? So that's something that you can do. Most machine learning models would use that as input. So feel free to just run that function in a composite before you send it to the classifier. So let's say we have a road network. I've uploaded OpenStreetMap roads to Earth Engine, and this is what I'm using here. And I want to say if my training sample is close to a road, I want to capture that. If it's far from the road, I want to capture that. You can run this function .distance on the road, and what you get is a raster like this, where the value of the raster is the distance to nearest road. And you can add this raster to your composite. And when you sample that, what you get is that in each feature, you'll have one more property called distance. So this point is 74 meters away from the nearest road. If I go to some other sample and say this point is 41 meters from the nearest road, so on. Right? So now I have a property that captures the distance to nearest road. And if there's a pattern, the classifier will learn from that. Okay, so the function here is called .distance, which is the the distance to nearest feature collection. And there's also a distance function that works for raster images. If you have a raster saying that this is water versus non-water, this is distance to nearest water object, for example. The next one, let's say I have a pixel. I want to know the value of surrounding pixels. So for example, look at it in this case. I'm trying to classify this pixel. Let's say there are 2 pixels here, but they are surrounded by different things. How can I capture the surroundings? There's a function here called neighborhood to bands. You can give it a kernel and it'll capture the neighborhood and turn them into bands. Let's see how that works. Once you run this, you get additional bands. For example, I've run this function on the NDVI band. So I've computed NDVI. So I get the NDVI of that pixel, but along with that, I get neighboring NDVIs. So I get 8 more NDVI values, NDVI of the left pixel, NDVI of the corner pixel, NDVI of the top pixel, and so on. And all of those are now bands. For each pixel, in the new band will be the value of its neighbor. Then the effect of that is when I sample that image, now I have multiple values of NDVI. This is the value of the pixel's NDVI, and this is the NDVI of the surrounding. And our model can learn from all of that. And if I uncomment everything here, you can see I'm now training a classifier on all of this spatial context because I've turned them into a table. I've turned the spatial context as bands, and when I've sampled my training data, I have all of those information. Each training sample has that information. The random forest will try to use that and say, how can I best use this to predict the class that I need to? And then you'll have your classified image that will be much better than without using the spatial context. You don't need to use all of this. Use whatever makes sense for your analysis and for the project. Next, one of the advanced techniques for geospatial machine learning is how to incorporate a time series. When you're trying to classify an image, sometimes just the pixel value it's not enough to distinguish 2 different pixels. Most common example for this is crops. Let's say you're trying to identify crop versus forest. They may have the same reflectance if you just consider the median value. They both look green. But now how do you separate them? Or you're trying to separate 2 crops which both look green. How do you separate them? The way to do this is to incorporate the whole history of the pixel, because the pixel has undergone change during a year or growing season or harvest season, and you want to capture that temporal context in your model so that model can say, hey, these 2 pixels have different history, and if I learn from the history, I can separate them. How to do this in the Earth Engine or how to do this for machine learning? Well, you have to turn the history of a pixel into a table. Let's see what are some of the techniques to do this. So how do you capture the time series variable as bands in your image? If you convert your time series into bands, you'll be able to use them as an input to your classifier. 2 main techniques. One is called seasonal composite. So you instead of doing a yearly composite, you just say, I will take 1 composite for each season, 1 for the growth season, 1 for the harvest season, 1 for the barren season, and so on. Whatever season makes sense for your crop that you're trying to classify. And then you use information from all of those composites as bands and use them in your classification. Let's see the example for this. Back to your repository in the supervised classification folder, we have a script, seasonal composite for crop classification. We are using the same area that we are trying to classify. This is in south of India. This part of the world, they follow different cropping season, and you need to capture those cropping season to be able to classify crops in this region better. So you start out the way you do. You start with the Sentinel collection. You apply the filters for the year that you want to classify. You do the cloud masking. After you cloud mask, don't do a median composite. Let's do different composites for different seasons. In this part of the world, they have 3 distinct seasons for cropping. One is the winter crops, there are summer crops, and then there are monsoon crops. So I can take one composite for January to March images, another composite for April to June, and another for July to December. And I can create a different composite. Here we just define those months as list and then map a function over it. So we can create one composite for each season. Let's see what those composites looks like. If I go to some region here, you'll see that the landscape looks very different in each of those seasons. This is what it looks like in winter. This is what it's in harvest season. And see there are changes here. And then in the monsoon season, it's again very green. You will see that it's just totally different. And if we had just done a median composite, we would totally miss that. So now instead of having just 12 bands of information, we have 12 bands of one season, 12 bands of another season, 12 bands of another season. You stack them together. So the function you would use is add bands. You can say take the first season composite, add bands from the second season, add bands from the third season. And now you have this 36 band composite. When you sample your training data from this composite, you'll get 36 values. What the pixel was in season 1, what the pixel was in season 2, and what the pixel was in season 3. And you need to predict the class based on those 36 values instead of 12. And the model will learn that if crop A is growing in the first season, values will be higher here. If the crop B is growing in summer, the values will be higher here. And you'll use those relevant bands to classify them. So you're just sending them more information and the model will learn from those information. And this is how you can incorporate time into your model by just doing seasonal composites. I want to share one example. I've linked to the paper in the slide here. If you're doing any kind of crop classification, do read this paper. It's a really interesting methodology and it shows you the standard technique of how you can do crop classification and incorporate time in your model. I want to show you the chart for the methodology. You can see the chart. They're using Landsat data and they're trying to distinguish coffee from other crops. So you're trying to map coffee. It's a crop classification. So again, just doing a median composite is not enough. So you say, I'll start with my data. I will do 4 composites: dry, hot season, rainy season, dry, cool season, and then 1 median composite for the entire year. So I've now done 4 composites. And coffee has different growth pattern in all of those 4. Different crops or forests will have a different growth pattern. And by giving this information, you are able to then separate out coffee. One of the problems that you'll see, we'll shortly learn how to deal with this, is now you may have 12 plus 12 plus 12 plus 12, 48 bands. And that is too much information for the classifier to learn. So you can compress the information by doing something called principal component analysis. You do this here. So you can say you will compress the information into less number of bands. You still retain all the information from the 48 bands, but you have much lesser bands to work for. And then you just say extract all the band values at training points, develop a random forest model, do the classification, and you have a final land cover map. So again, this paper employs the seasonal composite technique that I mentioned. And again, they say, okay, we also want to use elevation, slope, and aspect bands. Elevation is really important for coffee. Coffee grows at higher elevation, so you want to capture that for coffee as well. So again, any information that makes sense for your crop that will help it differentiate from other crop can be added here. So we learned about seasonal composite for crop classification. Here we are defining distinct seasons and say, if I want to do seasonal composite, what if I want to capture the full phenology? Maybe there are too many crops and each follow the different growth pattern. I can't distinguish them between seasons. How can I capture the exact phenology and use them for my classification? So that brings us to the next technique, which is called time series modeling. Here you don't create any composite. Here you say, I'll take the full time series of some value and most commonly used one is NDVI because it captures the vegetation growth. So we'll say, I'll take the full time series of NDVI, every observation that has occurred in a year at each pixel, and I'll try to model that with some mathematical formula. So instead of doing composite and getting the reflectance value, I said, I don't care about reflectance. I want to know what was the pattern and can I capture the pattern at each pixel? And if the pattern is similar to a neighboring pixel, then it's the same crop. If the pattern is different, then those two are different. That's called time series modeling. Again, very hard thing to do mathematically and hard thing computationally. Earth Engine makes it much easy to do. There's code available. I'm going to show you the code and now you can run it at scale because again, you don't have to download images. You don't have to extract the time series. You can just run it at each pixel. So let's see how to do this. The script is in the same folder called time series modeling. Here we start with a collection and we apply our filters, apply the cloud mask. Cloud mask is important because you don't want to capture cloud in your data. You want the real NDVI. And once you have your filtered and masked collection, you extract your time series at each pixel. And you can see this is what each pixel look like. This is over one farm. And you can see the pattern from 2019 to 2022, 3-year pattern. You can see some noise, but you can kind of see the pattern, right? There's a growth and harvest and growth and harvest and so on. If I want to incorporate each image's bands into my learning, I'll have 12 bands for hundreds of images, and that doesn't scale well. So instead of adding bands for reflectances for each image, I'll say, can I just model this using some function? Most of the time, NDVI looks like a sine wave or a cos wave. So can I say, can I fit a sine wave to this? This is also similar to Fourier transforms, where you have any signal and you decompose them into the sine and cos waves of a particular signal. So can I fit a sine curve to it? And you can fit this. The code is available here. You can just copy paste the code. And once you fit, only parameter you need to change is how many sine waves do you want to fit into? It's a single cropping, dual cropping per year. So per year, how many sine waves do you want to model this with? So here we are modeling 2 harmonics per year. And when you run this, you get something like this, that I had this time series. I've now fit sine wave to it, and I know how to describe the sine wave with a formula. I can uniquely describe the sine wave by using phase and amplitude, 2 numbers, and I can model this. And you can do this at each pixel. You can model the time series using phase and amplitude values at each pixel. If you have 2 harmonics, you'll have 2 phase and 2 amplitude values. If it's a one cycle per season, you'll have 1 phase and 1 amplitude value. Now, if you do this at every pixel and you compare 2 farms, which are very different crops, and you just show what the model looks like, you can see the model looks very different because the growth pattern of those 2 farms is very different. And the phase and amplitude value at those 2 places will be very different. You capture the full phenology of NDVI at those 2 pixels by this 2 parameters, phase and amplitude. And what we do when we do remote sensing machine learning, well, we say we have 1 phase value at each pixel. So we have a phase image, we have an amplitude image, let's add it to our composite. And when we sample that, the classifier will say, this is the phase, this is the amplitude, this is the class. And if those 2 are different for different crops, it can separate them. You can also visually see this. If we display phase and amplitude bands as an image, this is what you'll see. You can see this is the landscape, different crops growing in this region. I've taken 3-year Sentinel-2 NDVI time series, fit harmonic time series at each pixel, and displaying the results of phase and amplitude values at each pixel. If the colors will represent those combination of phase and amplitude. The colors at 2 pixels are same, that means they're growing the same crop. The colors are different, they are growing different crops. Once this loads, you will see different farms and different colors. The farms growing the same crop will be in the same color. And now if I add those bands to my composite, the classifier will be able to learn from this. This is a really robust technique that can capture the full phenology, can capture different kind of vegetations. So if you want to separate out grassland, shrubland, cropland, permanent forest, how do you do this? Well, just fit this harmonic time series, take those bands and send it to the classifier. The classifier with the training data will be able to learn from each of this and can separate them. Again, something like this is very computation intensive, but you can see you can now do this in Earth Engine. If you're doing this for your region, compute this, export this as an asset. And once your asset is computed, you can add it to a composite and do your machine learning with that. The next topic I want to cover is the topic of principal component analysis. When you are adding too much information to your model and say, I have bands for season 1, bands for season 2, bands for season 3, or I have added temperature band, I've added slope in elevation band. And as you add more and more information, the classifier finds it much difficult to discover the true pattern. It has to say, I have 500 columns of information that I need to learn from and predict this class. And each column, each feature is sending a very weak signal of how it is related to the output. So in machine learning, this thing is called curse of dimensionality. If you have multi-dimensional data, the more dimensions you add to your data, the classifier finds it harder and harder to learn. And if you test the accuracy of a model, you keep adding more bands to your composite, at some point the accuracy will start going down. So the classifier just can't learn from so much data. So I want to use all the information. The information is important, but how do I reduce the dimensions of the data? So how do I compress all of this hundreds of bands of information into smaller number of bands by reducing the dimensionality? The main technique that you use is called PCA. This is a statistical technique which says, I have this information, can I compress it into information where I retain most of the information that was there in the original bands, but I'll have much fewer bands. The way they do this is you say, I have two bands which might be correlated. Let's say I have band 1 and band 2. Whenever the band 1 is 10, band 2 is 20. Whenever the band 1 is 20, the band 2 is 40. Everybody is like this. So I said, why do I need two bands? They are all having the same information. They all have this, they're correlated. Whenever this band 1 goes up, band 2 goes up by the same amount. Why do I need two bands? I can remove information from band 2, and I can have only the bands which are uncorrelated, and I can still retain all the information. And this is the kind of core concept of PCA. When you run PCA, it'll try to extract all the uncorrelated information from your image and give you fewer bands which have most of the information. And in remote sensing, you say, whenever you say I have 12 band image, I do PCA, I'll get 12 PCA bands. I'll get principal component 1, principal component 2, principal component 3, and up to 12. But most of the information that was there in the 12 bands will be in the first 2 or 3 bands. So you say, I'll not use all the PCA bands, I'll just use the first 3 PCA bands and use that for my classification. I'll still retain like 99% of the information. So my classifier can still separate out and do all the work, but it has got much fewer dimensions to work with. Let's see how this works in practice. You have the script in your supplement. So here, let's say we have this 12-band composite, and we want to use this. Let's say you have a seasonal composite, you have 4 such composites, and you want to use them for machine learning. And you don't want to send 48 bands to your classifier. You want to say, I have these 12 bands. Some of these bands are correlated, right? There's a red band and a red edge band, or there is, this SWR1 and SWR2. Most of them will be having some information which is duplicate. Can I compress that? So we have a function written for you here called PCA. Take an input image, return the PCA for that. So here we just call the function on the composite, we return the PCA image. Let's run this. So we take this 12-band image, run the principal component analysis on this, and you get 12 principal component bands. If we compute the variance that was captured by each PCA band, the output of the analysis says the first band of principal component captures 68% of the variance that was present in the 12 bands. The second band captured 22%, third band 5.6%, and so on. The 12 band doesn't have 0. It has still some information, right? But you can safely say, I will just use first 3, and I've captured like 98% of the variance. And I'll send only the first 3 PCA bands to my classifier. And my classifier now can work with much richer data, which is uncorrelated. Each band will have unique information, and it'll be uniquely correlated with the output. And it just performs much better. If I just take the first 3 PCA bands and take that image and display this on the map, you'll see how the image looks. So at the bottom is the RGB image, and on the top is the principal component image, just the 3 bands. This is the image that was captured by Sentinel-2, and this is the information that is captured in all 12 bands. You can see it correlates quite well with that. It also has so much information in this. But now you have only 3 bands, and the classifier will only see these 3 bands, and it'll try to use that for your classification. So you do the PCA, and at the end you only take the first 3 PCA bands and then add that to your composite. In my experience, this is the magic bullet to fix your classification issues. Every time there's a classification problem, you do PCA, suddenly your accuracy jumps 5%, 10%, and so on. So this really helps the model learn much better. You can apply this in all contexts. For example, if you want to add texture to your image, you compute texture, you get 17 bands. You don't know which one is important. Do PCA on those texture bands, send only those 3 bands to your composite. You're doing seasonal composite, for each season, just do PCA for that season and add that to your main composite. And that really helps the model learn from the features that are really important, and you should see much improved accuracy. Okay, we are done with this. Your supplement contains a lot more scripts. Whenever you have a question related to supervised classification, how do I plot spectral curves? How do I identify GCPs which are misclassified? How do I do stratified sampling? Look in your supplement, you'll find a script. Whenever somebody asks me a question and I can't find a script, I create one and put it in the supplement. So the supplement contains answers to all your questions. So first check that, and you're likely going to find an answer to your classification problem. I've also linked to some references to read these papers specific to classification. These are the selections that will give you some good idea of how people use machine learning in practice on remote sensing.